Hello there, and welcome to Midnight Geography. Tonight we'll drift into the landscapes of Idaho. Idaho is where the earth remembers its fire. It's a place where ancient lava fields stretch beneath stars, where rivers carve the deepest gorges on the continent, where stone formations rise like cathedrals in silence. Here the ground still breathes with hot springs, and mountains hold names in languages nearly forgotten. Idaho is geology's quiet museum, a state where violence became beauty, where destruction carved wonder, and where the planet's restless past settled into contemplation. If you enjoy these peaceful geographical explorations, consider liking and subscribing. It helps other curious minds find their way here too. But for now, let's begin. The Craters of the Moon. National Monument spreads across 618 square miles of southern Idaho like a frozen ocean of stone. These volcanic formations were born between 15,000 and 2,000 years ago, making them among the youngest lava fields in the continental United States. Walk through this landscape, and you're traversing rock that cooled while humans were already painting on cave walls, already domesticating animals, already building civilizations across distant continents. The lava here didn't erupt in a single catastrophic event, but rather seeped and flowed across millennia, each eruption adding another layer to this monument of patient geology. The surface is textured with formations called pressure ridges and squeeze-ups, where cooling lava buckled and wrinkled like fabric. At night, under the absence of city lights, this dark landscape becomes one of the finest places in America to observe stars, the black basalt absorbing what little light exists, leaving only the heavens visible above. 280 miles northeast of those frozen lava waves, the Lost River Range rises into thin mountain air. Here stands Bora Peak, Idaho's highest point, reaching 12,662 feet toward the sky. But what makes Bora particularly remarkable is that it grew during human memory. In October of 1983, a magnitude 7 earthquake struck near the mountain's base, and when the trembling stopped, Bora Peak stood 6 feet taller than before. The earthquake created a visible fault scarp along the mountain's western flank, a scar in the earth 21 miles long where the ground literally ripped apart and shifted upward. This is geology happening not in the deep past, but in the present tense, a reminder that mountains are not eternal monuments, but active participants in the Earth's ongoing conversation with itself. The summit still accumulates snow well into July, each winter adding its white blanket to a peak that may, someday, grow taller still. Beneath the town of Lava Hot Springs, the Earth remembers its heat. Geothermal water rises from depths exceeding 2 miles, having traveled through fractured rock warmed by the planet's interior furnace. This water emerges at temperatures reaching 112 degrees Fahrenheit, naturally heated by proximity to magma chambers that still simmer far below Idaho's surface. The springs have been used for thousands of years, first by indigenous peoples who considered them healing waters, later by settlers who built bathhouses to capture their warmth. The water contains dissolved minerals accumulated during its subterranean journey: calcium, sulfur, trace elements that give it a distinctive quality. What's remarkable is the sheer volume flowing upward constantly, day after day, year after year, as if the earth is breathing steam through these natural vents. In winter, when air temperatures plunge below zero, the springs continue releasing their heat, creating pockets of warmth in an otherwise frozen landscape. The Bruneau Canyon reveals itself slowly to those who seek it. Carved by the Bruneau River over countless millennia, this chasm reaches depths of 1,200 feet, yet it remains so remote that many Idaho residents live their entire lives without witnessing its grandeur. The canyon walls expose layers of volcanic ash and rhyolite, each stratum representing ancient eruptions from the Yellowstone hotspot. The river at the bottom runs green in certain lights, colored by minerals dissolved from the canyon walls during spring floods. Birds nest on ledges hundreds of feet above the water, and in spring, wildflowers bloom on slopes that see sunshine for only a few hours each day. The isolation of Bruneau Canyon is part of its character. There are no grand overlooks with parking lots, no railings or interpretive signs. It simply exists in the high desert of southwestern Idaho, known primarily to geologists, rafters, and those who study the quiet places where water has written its story in stone over millions of patient years. Shoshone Falls commands the Snake River with undeniable presence. This waterfall drops 212 feet, making it 45 feet taller than Niagara Falls, though few beyond Idaho know its name. The falls were formed when the Bonneville Flood, approximately 14,000 years ago, carved through basalt layers in catastrophic volumes. Ancient lava flows created the resistant caprock that forms the fall's lip, while softer sediments beneath eroded more quickly, creating the characteristic overhang. During spring runoff, when snowmelt from distant mountains swells the Snake River, Shoshone Falls becomes a thundering curtain of white water stretching hundreds of feet across. But by late summer, much of the river's flow is diverted upstream for agricultural irrigation, and the falls can diminish to a relative trickle. This seasonal transformation reveals humanity's ongoing negotiation with natural systems, the choice between letting water flow freely and redirecting it to make deserts bloom. The falls remain magnificent even in their reduced state, a reminder of the forces that shaped this landscape. The City of Rocks National Reserve exists as if someone collected giant marbles of granite and scattered them across sagebrush hills. These formations, some reaching 2.5 billion years old, represent some of the oldest rock in North America. They began as molten magma that cooled slowly deep underground, forming granite with large mineral crystals. Over eons, as overlying rock eroded away, the granite was exposed to wind and water. The peculiar rounded shapes come from a process called spheroidal weathering, where water seeps into cracks and dissolves minerals along joint lines, gradually smoothing corners into curves. Early emigrants on the California Trail passed through here in the 1800s, and many carved their names into the soft granite, inscriptions still visible today. The formations have names like Bath Rock and Bread Loaves, descriptive terms that capture their whimsical shapes. At sunrise and sunset, the granite glows warm orange and pink, ancient stone catching contemporary light, unchanged in essence, but eternally changing in appearance as shadows shift and seasons turn. Lake Pen Oreille rests in northern Idaho like a liquid jewel held in mountain hands. The lake reaches depths of 1,150 feet, making it Idaho's deepest lake and the 5th deepest in the United States. Its profound depth comes from glacial carving during the last ice age, when massive sheets of ice scoured the Purcell Trench, gouging the basin that would eventually fill with water. The lake's name comes from French fur traders who encountered local Kalispel people wearing shell earrings, pont d'oreille, meaning hangs from ears in French. What makes this lake particularly unusual is its use during World War II. The U.S. Navy operated a submarine testing facility here, chosen specifically because its depth and acoustic properties resembled ocean conditions better than any other inland body of water in North America. Today, the lake remains extraordinarily clear in places, its cold depths supporting lake trout that can live for decades and grow to remarkable sizes in the perpetual darkness far below the surface. Near the town of Arco, the earth has torn itself open in a wound that refuses to heal. The Great Rift stretches 62 miles across the Snake River Plain, a volcanic fissure where magma once rose from depths. Some sections of this crack are wide enough to swallow houses, their dark interiors descending into unknown depths. The rift formed during eruptions at craters of the moon, serving as the conduit through which lava flowed to the surface. Walking along the rift's edge, you can see into its depths, layers of cooled lava, collapsed tubes, and fractured basalt. The fissure remains as it was left thousands of years ago, a permanent scar documenting the violence of Idaho's volcanic past. In some places, the crack is narrow enough to step across. In others, it yawns wide enough that you cannot see the opposite rim. Snow accumulates in its protected depths and can persist into summer, creating microenvironments where ice exists while the surface above bakes under desert sun. The Great Rift is geology made visible, the planet's anatomy exposed. The town of Stanley occupies the Sawtooth Valley at an elevation of 6,260 feet, nestled between mountain ranges in a high basin that tests the limits of human habitation. Winter arrives early here and departs late, with temperatures that have plunged to minus 54 degrees Fahrenheit, making Stanley one of the coldest continuously inhabited places in the lower 48 states. The valley acts as a cold sink where frigid air settles and accumulates, unable to escape the surrounding peaks. On the coldest nights, ice fog forms from moisture in the air, crystallizing directly into frozen particles, creating an ethereal landscape where trees emerge from whiteness like ghosts. The growing season lasts barely 2 months, and residents burn firewood into June. Yet people choose to live here, drawn by the raw beauty of isolation, by meadows filled with wildflowers during brief summers, by the Salmon River flowing clear and cold through granite canyons, by skies so dark that the Milky Way casts shadows. Balanced Rock stands in Gooding County as if defying both gravity and common sense. This formation rises 48 feet into the air, a 40-ton boulder perched impossibly on a pedestal only 3 feet wide at its narrowest point. The rock formed from volcanic tuff, compressed ash that hardened into stone over millions of years. As softer material surrounding the formation eroded away, this particular column resisted weathering slightly better than its surroundings, though the top eroded faster than the base, creating the precarious appearance. Engineers have studied balanced rock and calculated that it should, theoretically, be stable given the weight distribution and friction coefficients involved, yet it appears so improbable that you want to push it to test whether it might topple. Indigenous peoples knew this formation for generations before settlers arrived, and it has stood through countless earthquakes that have toppled other formations. Eventually, in geological time, it will fall. Wind and rain and frost will find its weak point. But for now, it stands as a monument to the temporary permanence of stone. The Salmon River flows 425 miles through central Idaho's wilderness, earning its nickname, the River of No Return, from the difficulty early boaters faced trying to navigate upstream against its powerful current. What makes this river particularly remarkable is a stretch exceeding 180 miles where no bridge crosses its middle section. For nearly 200 miles of its length, the river flows through roadless wilderness, accessible only by trail or by boat. The canyon it has carved through the Idaho batholith reaches depths of more than a mile in places, with walls so steep that trees growing on the slopes appear tiny from the river's surface. Rapids punctuate the river's course, some named for the explorers who first ran them, others for the geological features that create them. The water runs clear green in some sections, reflecting the granite it flows over, while in other stretches it turns brown with silt after rainstorms send sediment down tributary creeks. This is one of the last major rivers in the continental United States, where long stretches remain essentially as they were before European contact, flowing wild and unmanaged. Minnetonka Cave burrows into the limestone flanks of the Bear River Range near Bear Lake, a 9-chamber system reaching 300 feet beneath the surface. The cave formed as slightly acidic water dissolved calcium carbonate in the limestone over hundreds of thousands of years, creating passages and rooms in the soluble rock. Inside, formations grow at the pace of geological patience, stalactites hanging from ceilings, stalagmites rising from floors, sometimes meeting after millennia to form columns. These features expand less than a cubic inch per century, each drip of mineral-laden water leaving behind a microscopic deposit of calcite. The cave maintains a constant temperature year-round, cool enough that visitors need jackets even in summer. The formations have colors: rust red from iron oxide, white from pure calcite, occasional streaks of black from manganese. Early visitors broke off pieces as souvenirs before the cave gained protection, and you can still see the damage. Formations snapped off decades ago that will take thousands of years to regrow even partially. The cave is a library of water and time. Each formation, a volume written drip by patient drip. The Owyhee Canyonlands sprawl across more than 3 million acres of southwestern Idaho, a landscape of volcanic rock carved into maze-like canyon systems. Stone walls rise 1,000 feet from desert floors, their surfaces banded with layers of ash and basalt from ancient eruptions. The canyons carry names like Jarbidge, Bruneau, and Sheep Creek, each one a separate tributary system cutting through the high desert plateau. This is among the most remote regions in the contiguous United States, with fewer roads per square mile than almost anywhere else outside Alaska. The rock here tells stories of the Yellowstone hotspot's westward migration, each layer representing eruptions from different periods as the North American plate moved over the stationary magma plume below. Ravens nest on cliff faces, and bighorn sheep navigate impossible-looking ledges with casual confidence. In some canyons, springs emerge where water that fell as rain or snow decades ago finally surfaces after traveling through fractured rock. The Owyhees remain largely unknown even to Idaho residents, a secret held in plain sight simply by virtue of distance and difficulty. Bear Lake straddles the border between Idaho and Utah, its unusual turquoise color immediately distinguishing it from typical mountain lakes. The color comes from suspended limestone particles so fine they remain in suspension rather than settling, reflecting blue-green wavelengths of light in a phenomenon similar to tropical waters, though this lake sits at 6,000 feet elevation. The lake formed when glacial and river deposits blocked drainage from the valley, creating a natural reservoir that has persisted for over 28,000 years. Its age and isolation have allowed unique species to evolve. The Bonneville cisco, a fish found nowhere else on Earth, swims in schools beneath the turquoise surface. The lake is relatively shallow for its size, averaging just 21 feet deep, though some areas reach depths of 200 feet. Mormon settlers in the 1800s named it for their leader, but indigenous peoples knew it long before, fishing its waters for species that exist only here. The turquoise water seems almost artificial in its intensity, as if someone added dye, but it's entirely natural, a quirk of geology and water chemistry creating beauty through physics. The Snake River Plain volcanic province has produced 3 massive calderas over the past 12 million years, eruptions so violent they dwarf anything in recorded human history. Each explosion was hundreds of times more powerful than the Mount St. Helens eruption of 1980. These caldera-forming events occurred as the Yellowstone hotspot moved northeast relative to the North American plate, leaving a trail of volcanic destruction that eventually became the Snake River Plain. The Haida volcanic field, the Pacabo volcanic field, and the Kilgore volcanic field each collapsed after their magma chambers emptied explosively, creating depressions that later filled with lava flows. Today, crops grow on soil formed from volcanic ash, and cities sit on ground that was molten rock comparatively recently in geological time. The next caldera in this sequence already exists beneath Yellowstone National Park, where magma continues accumulating, where geysers and hot springs reveal the heat still present below. The Snake River Plain is not dormant, but merely resting, a reminder that the Earth's most powerful forces operate on schedules measured in millennia. Dirkus Lake sits near Twin Falls, a body of water that exists by accident rather than design. In 1920, irrigation water diverted from the Snake River began seeping through porous volcanic rock, collecting in a natural depression that had previously been dry. Over time, the seepage filled this basin, creating a lake where none had existed before. The water maintains consistent clarity because it's filtered through layers of basalt before emerging into the lake basin. Today, the lake serves as a local recreation spot, though few visitors realize they're swimming in what is essentially a side effect of agricultural water management. The lake's existence depends on continued irrigation upstream. If the water diversion stopped, the lake would gradually drain away through the same porous rock that allowed it to form. It's a reminder of how human modifications to water systems can create new landscapes, sometimes intentionally and sometimes as unintended consequences. The lake has developed its own ecosystem now, with fish introduced by fisheries managers and aquatic plants establishing themselves in the filtered water, creating something that appears natural but is fundamentally artificial. The Sawtooth Mountains rise in central Idaho like the teeth of a massive saw blade laid against the sky, 57 peaks exceeding 10,000 feet in elevation. These mountains acquired their jagged profiles through glacial carving during ice ages that ended only 12,000 years ago. Alpine glaciers formed in cirques on north-facing slopes, slowly grinding away at the rock, carving U-shaped valleys between sharp arêtes and horn peaks. The granite here formed deep underground and was later uplifted and exposed by erosion, creating the light-colored rock that characterizes the range. Snow lingers on high peaks into August, and some years it never entirely melts, creating the conditions necessary for small glaciers to reform. Alpine lakes dot the high country, many of them still partially ice-covered in early July, their waters so cold and clear you can see 20 feet down to granite boulders on their bottoms. The Sawtooths are young mountains in geological terms, still being lifted by tectonic forces even as erosion works to wear them down, an ongoing competition between uplift and weathering that will continue for millions of years. Redfish Lake rests at 6,547 feet elevation in a glacially carved valley below the Sawtooth Mountains. The lake earned its name from sockeye salmon that once turned its waters crimson during spawning runs. More than 30,000 fish arriving each year after journeying 900 miles from the Pacific Ocean. The salmon would swim up the Columbia River, then the Snake, then the Salmon River, finally reaching this high alpine lake to spawn and die. But dam construction on the Columbia and Snake Rivers decimated the runs, and by the 1990s, fewer than 10 fish were returning annually. Extensive recovery efforts have increased numbers somewhat, but the massive runs that gave the lake its name may never return. The lake itself remains beautiful, its waters cold and clear, surrounded by granite peaks and dense forests. Native cutthroat trout still inhabit its depths, along with introduced lake trout that have complicated recovery efforts for the salmon. Redfish Lake holds memory in its name, a reminder of abundance lost, of cycles broken, of what happens when we fragment the pathways that species have followed for millennia. The Malad River cuts through limestone country southeast of Hagerman, creating gorges where the entire river periodically disappears and reappears. At a feature called Devil's Wash Bowl, the river vanishes into a limestone cavity carved by water dissolving soluble rock over thousands of years. The river drops into this natural drain, travels 400 feet through underground channels, then emerges downstream as if nothing unusual had occurred. The disappearance is complete. During certain flow conditions, you can stand at the dry riverbed downstream of the wash bowl and see no water, while just upstream the river flows normally. This phenomenon occurs in limestone karst topography, where water creates caves and passages underground through chemical weathering. The river's route through these passages has been mapped by dye tracing studies, following colored water through the subterranean system. The rock here is from ancient oceans that covered this region hundreds of millions of years ago. Limestone formed from accumulated shells and marine organisms, now being slowly dissolved and carried away, particle by particle, by the patient work of running water. The Malad River demonstrates that not all rivers stay above ground, that some choose to travel through the earth itself. Priest Lake occupies northern Idaho's panhandle, its upper section containing 25 miles of shoreline accessible only by boat or trail, with no road encircling it. This remote portion of the lake exists as it has for thousands of years: forested slopes descending to clear water, beaches of smooth stones, and channels between islands where osprey nest in tall pines. The lake formed when glacial deposits blocked drainage from the valley, creating a basin that filled with snowmelt and rain. Its waters are remarkably clear, fed by mountain streams carrying minimal sediment. The isolation of the upper lake has preserved it from development that surrounds more accessible waters. Fishermen reach hidden coves by boat, pulling northern pike and lake trout from depths where sunlight fades to darkness. In winter, when ice thick enough to support weight forms across the upper lake, the silence becomes absolute. No motors, no voices, just wind and pine branches, and the occasional crack of expanding ice. The lake demonstrates how accessibility shapes landscapes. The lower lake, reached by paved roads, hosts marinas and vacation homes, while the upper lake remains essentially wilderness, the same water but different worlds, separated merely by difficulty of access. The Bitterroot Range defines Idaho's eastern border with Montana, a high barrier of peaks where weather refuses to follow summer's rules. Snow can fall here in any month of the year, even in late July when valleys below swelter in heat. The range rises above 10,000 feet in multiple locations, high enough that winter never entirely releases its grip. Alpine meadows might bloom with wildflowers in August, only to be dusted with fresh snow the next morning, creating surreal landscapes where summer and winter coexist within hours. These mountains force moisture from passing weather systems, wringing precipitation from clouds that have crossed hundreds of miles of dry terrain. The result is a wet barrier in an otherwise arid region, forests thick with spruce and fir clinging to slopes where avalanche paths scar the vegetation. Indigenous peoples cross these mountains on ancient trails, following ridge lines above the tree line, where travel was easier than bushwhacking through dense forest. The range's name comes from a plant, bitterroot, whose pink flowers bloom briefly each spring, a native species that Salish peoples harvested for food. The mountains hold that dichotomy, bitter and beautiful, harsh and essential, a place where summer is merely a suggestion winter tolerates temporarily. Thousand Springs emerges along a stretch of the Snake River Canyon near Hagerman, where water that fell as rain or snow decades ago finally surfaces after traveling through underground aquifer systems. The springs release 3.8 million gallons per minute during peak flow, an almost incomprehensible volume pouring from canyon walls in hundreds of separate outlets. Some springs emerge as single jets strong enough to create whirlpools where they hit the river below. Others seep from moss-covered walls and sheets of water that catch sunlight and create rainbows in their mist. The water maintaining these springs fell on the Snake River Plain up to 300 miles away, percolated down through porous basalt, traveled horizontally through aquifer layers, and finally emerged here, where the canyon cuts deep enough to intersect the water table. The journey can take 50 to 100 years, depending on the path, meaning the water flowing from Thousand Springs today began its underground journey during World War I or before. Early settlers harnessed some of these springs for fish hatcheries, using the constant cold temperature and abundant flow to raise trout. Today, much of the aquifer feeding these springs is depleted by agricultural pumping, and flow rates have diminished from historical peaks. But Thousand Springs remains one of the most remarkable displays of groundwater emergence in North America. The Menon Buttes rise as twin volcanic cones near Rexburg, formations created through violent interaction between rising magma and underground water 10,000 years ago. When molten rock encountered saturated sediments beneath the Snake River Plain, the water flashed instantly to steam, creating explosive eruptions that hurled volcanic ash and rock fragments into the air. These explosions built the buttes, layer by layer, each eruption adding another stratum of volcanic tuff. The buttes stand about 800 feet above the surrounding plain, steep-sided and surprisingly symmetrical given their violent birth. The North Butte is slightly taller, and both show clear crater depressions at their summits, where the last eruptions occurred. Unlike most volcanic features in Idaho that formed from basaltic lava, the Menon Buttes are tuff cones, made primarily of consolidated ash rather than solid lava rock. This makes them relatively soft and susceptible to erosion. In 10,000 years, they've already lost significant height from wind and water weathering. Vegetation covers their slopes now, sagebrush and grasses that have established themselves in the volcanic soil. Local residents use the buttes as landmarks visible for miles across the flat Snake River Plain, two identical twins marking where the earth briefly exploded from internal pressures that have since gone quiet. Wilson Butte Cave opens in a basalt hillside near Twin Falls, its entrance unassuming, but its contents extraordinary. Excavations in this cave have uncovered artifacts showing human habitation from 14,500 years ago, placing it among the oldest evidence of human presence in North America. The people who sheltered here witnessed the end of the last ice age, hunted megafauna that are now extinct, and left behind stone tools worked with techniques that would be used for thousands of years afterward. The cave itself formed as a lava tube, a channel where molten rock once flowed through, while the surface above cooled and solidified. When the lava drained away, it left this hollow passage, and eventually wind and erosion exposed an entrance. The volcanic rock walls provided protection from weather and predators, and the cave's depth maintained relatively stable temperatures year-round. Archaeologists working carefully through layers of sediment found evidence of multiple occupations spanning thousands of years, different groups returning to the same shelter across generations so distant they would have been unrecognizable to each other. The cave is closed to public access now, protected so that future researchers with better techniques can continue studying what remains. But it stands as proof that humans walked Idaho's landscapes while glaciers still lingered in northern valleys. The Selway River drops 6,680 feet over its 100-mile course through the Bitterroot Mountains, creating some of the most challenging whitewater in the United States. The river begins as snowmelt in high cirques, gathering volume as tributary streams join from side canyons, building power as gradient steepens. The gradient averages more than 60 feet per mile, though in some sections, the drop is far steeper, creating rapids rated at the highest difficulty levels. Boulders the size of houses crowd the river channel, creating hydraulic features where water behaves in ways that seem to violate physics, reversing course, forming standing waves, creating holes that can trap boats in recirculating currents. The canyon walls rise steeply on both sides, forested with cedar and pine that somehow find purchase on near vertical slopes. There are no roads along most of the Selway. Rafters and kayakers who run the river enter a wilderness accessible only by water or trail, committing to days of downstream travel with no option to exit early. The river's name comes from a corruption of a Nez Perce word, though the exact meaning has been lost to time. What remains is the river itself, dropping through stone and forest, a ribbon of white water, tracing the fastest route between high mountains and lower valleys. Craters of the Moon contains more than 25 volcanic cones scattered across its lava fields, though most visitors see only the few nearest the main road and paved trail. The other cones rise in the wilderness portion of the monument, accessible only to those willing to hike across rough lava that tears at boot soles and requires constant attention to foot placement. Each cone represents a separate vent where lava emerged during eruptions spanning thousands of years. Some are symmetrical cinder cones built from fragments of lava hurled into the air and falling back around the vent. Others are spatter cones, smaller features created when semi-molten lava landed still soft enough to weld together. The cones range from mere bumps in the lava to prominent features rising hundreds of feet above surrounding flows. Walking among them is like exploring a workshop where the earth experimented with different designs, each cone a unique variation on the theme of molten rock reaching the surface. Many cones have summit craters you can peer into, seeing the throat where lava last rose. In winter, snow collects in these craters, creating temporary lakes that melt away each spring. The cones will never erupt again. The volcanic system that created them has moved on, but they remain as monuments to processes that built much of southern Idaho. The Lost River earns its name through disappearance. Near Arco, this river flowing down from the Lost River Range encounters the porous lava rock of the Snake River Plain and simply vanishes, sinking into the ground as if someone pulled a plug. The river travels underground for miles, flowing through spaces between basalt cobbles and fractured rock layers, eventually re-emerging as springs along the Snake River, dozens of miles away. The process is called infiltration, and it happens because the lava rock here is so fractured and porous that it cannot hold water on the surface. Early settlers were baffled by this river that ceased to exist, that flowed strong from mountain canyons only to disappear into dry ground. They gave it various names: lost, sunk, vanished, all trying to describe water's refusal to stay visible. During spring runoff, when snowmelt swells the river beyond the ground's capacity to absorb it, the Lost River sometimes flows past its usual sinking point, creating a temporary surface stream. But most years, it vanishes as reliably as sunrise. contributing its water to the massive aquifer beneath the Snake River plain, becoming indistinguishable from rain that fell 50 miles away or irrigation return flow from farms. The river demonstrates that not all water follows obvious paths, that sometimes the most important flows happen where we cannot see them. Castle Peak rises in the White Cloud Mountains to 11,815 feet, its summit plateau covered with limestone that once formed the bottom of an ancient sea. 300 million years ago, when the supercontinent Pangaea was still assembling, this region lay beneath tropical ocean waters where marine organisms lived, died, and accumulated on the seafloor. Their shells and skeletons, composed of calcium carbonate, eventually compressed into limestone rock. Then tectonic forces uplifted these seafloor deposits thousands of feet into the air, folding and fracturing the rock, tilting what was horizontal into steep mountain slopes. Today, you can find fossils of marine creatures at Castle Peak's summit, evidence of ocean life at an elevation where only the hardiest alpine plants now grow. The peak's name comes from its appearance from certain angles, where rock formations create battlements and towers reminiscent of medieval fortifications. Snow lingers on the northern exposures into August, and the limestone weathers into intricate patterns where water has dissolved mineral grains. Standing on Castle Peak's summit, surrounded by fossil remains of ancient seas, you occupy two times simultaneously: the deep past when warm waters covered what is now Idaho, and the present moment where cold winds sweep across mountain stone. The limestone will eventually erode away, returning its minerals to rivers that carry them toward modern oceans, completing cycles that span hundreds of millions of years. The Portneuf Range, southeast of Pocatello, demonstrates geological forces with unusual clarity. These are fold mountains, where entire layers of rock have been bent into waves by tectonic pressure as the Earth's crust compressed. You can see this in cliff faces where sedimentary layers that should be horizontal are instead tilted, folded, sometimes even turned completely vertical. The folds have names: anticlines where rock arches upward, synclines where rock sags downward, descriptive terms that capture stone's unexpected fluidity when enough pressure and time combine. The Portneuf Range formed as the North American plate was compressed from various directions, squeezing rock layers like fabric gathered in a fist. Some folds are gentle undulations spanning miles. Others are tight switchbacks, where rock layers reverse direction within feet. Geologists study these mountains to understand how rocks behave under stress, how brittle materials can fold instead of breaking when force is applied slowly enough. The range is not particularly high. Peaks barely exceed 9,000 feet, but its geological story is written plainly in every exposed cliff. Limestone, sandstone, and shale layers tell of ancient environments: shallow seas, coastal plains, river deltas, all now tilted and folded into mountain form, raised high above the valley floors where Pocatello's residents go about daily life, rarely looking up at the waves of stone frozen above them. Henry's Fork of the Snake River maintains water temperatures between 50 and 60 degrees Fahrenheit year-round, an unusual constancy that makes it one of Idaho's most productive trout fisheries. The temperature stability comes from springs fed by the eastern Snake River Plain aquifer, where water travels through volcanic rock insulated from seasonal temperature swings. These springs release water at the temperature the aquifer maintains, cool but not cold, and their flow is consistent enough that the river rarely freezes even during severe winters. The constant temperature creates ideal conditions for aquatic insects that form the base of the river's food web. Mayflies, caddisflies, and stoneflies thrive in the stable conditions, and trout grow large, feeding on this abundant insect life. Anglers travel from around the world to fish Henry's Fork, particularly the section below Island Park Dam, where spring influences are strongest. The river flows through meadows and beneath volcanic mesas, its clear water revealing trout holding in current, rising to sip insects from the surface. The springs that feed Henry's Fork are part of the same aquifer system that produces Thousand Springs miles downstream. Water following underground paths through porous basalt, traveling for decades before emerging into daylight. The river's name honors Andrew Henry, a fur trader who worked this region in the early 1800s, though indigenous peoples fished these waters for thousands of years before Europeans arrived and applied their own names. The silent city of rocks occupies a remote section of the Albion Mountains, a formation where natural stone corridors create unexpected acoustic effects. The granite here has weathered into narrow passages between towering rock formations, and sound behaves strangely in these spaces. Whispers carry hundreds of feet, amplified and channeled by rock walls. Conversations echo and repeat, sometimes seeming to come from directions they didn't originate. The acoustic properties occur because the rock corridors create natural sound tubes, channeling acoustic waves and reflecting them in ways that open spaces never could. Early visitors noted the peculiar quality, how voices seemed louder than they should be, how sounds persisted longer than expected. The Silent City name, despite the acoustic amplification, comes from the appearance of the formations, towers and walls arranged like buildings in an abandoned city, creating the impression of architecture despite being entirely natural. The granite is part of the same Albion Range batholith that created the City of Rocks, formed deep underground and later exposed by erosion. But this section has weathered into narrower passages, creating the conditions for sound to behave unusually. Walking through the Silent City, you become aware of every footstep, every breath, every small noise amplified by stone into something larger. It's a place that makes you conscious of sound in ways that normal landscapes never do, where silence itself becomes an acoustic presence. Lake Coeur d'Alene spreads across 49 square miles of northern Idaho, yet its average depth is only 44 feet, a broad, shallow lake formed when glacial deposits dammed the Coeur d'Alene River during the last ice age. The lake's shallowness makes it responsive to seasonal changes. In spring, when snowmelt swells tributary rivers, the lake level can rise several feet, flooding low-lying areas and expanding its surface area. In late summer, after irrigation withdrawals and evaporation, the lake shrinks back to a smaller footprint. The shallow water warms quickly in summer, creating conditions where algae blooms can develop, turning sections of the clear water green. The lake's name comes from French fur traders who encountered the Coeur d'Alene tribe, the name supposedly meaning heart of an awl, either a reference to sharp trading practices or a mistranslation of the tribal name for themselves. The lake has a complex history of mining pollution, as tributary streams carried heavy metals from silver and lead mines in the Coeur d'Alene mining district upstream. Cleanup efforts have removed some contaminated sediments, but traces remain in the lake bed, a reminder that landscapes remember what humans do to them. Despite pollution history, the lake remains popular for recreation, its broad surface perfect for sailboats that can find wind without worrying about sudden depth changes. The shallow water also means the entire lake turns over seasonally, mixing surface and bottom waters in ways that deeper lakes never do completely. The Big Wood River flows through Sun Valley and the surrounding mountains, maintaining flows even during drought years when many Idaho rivers diminish to trickles. The river's reliability comes from snowpack in the Pioneer Mountains, where annual accumulation can reach 200 inches or more at higher elevations. This deep snow melts slowly through spring and into summer, releasing water gradually rather than all at once. The watershed is mostly undeveloped, high peaks, alpine basins, and forest, so snowmelt reaches the river with minimal interception by human uses. The river's name is a translation from Shoshone language, referring to the driftwood that accumulates along its banks during spring floods. Early trappers and settlers adopted the indigenous name, preferring it to the generic titles they often imposed on unfamiliar landscapes. The river runs clear most of the year, fed by springs and snowmelt, though during peak runoff in late May, it turns brown with suspended sediment. Trout thrive in the Big Wood, native species joined by introduced rainbows and browns. The river carved the valley where Sun Valley developed as a ski resort in the 1930s, chosen specifically for the reliable snowfall that the Pioneer Mountains generated. Today, the river flows past expensive homes and through working ranches, its waters allocated and measured, yet still sustained by mountain snowpack that accumulates beyond human control. Indian bathtubs near Brunot are natural depressions carved into solid rock by wind, carrying sand particles like liquid sandpaper. These smooth, bowl-shaped hollows range from inches to several feet deep, worn into exposed sandstone over thousands of years of abrasion. The process requires specific conditions: exposed rock, steady wind patterns, and a supply of sand particles that act as cutting agents. Wind alone cannot carve stone, but wind-carrying sand becomes an erosive force capable of wearing away even resistant rock. The depressions form where initial irregularities in the rock catch blowing sand, creating small pockets where sand swirls and grinds against stone. Once started, the process becomes self-reinforcing. The depression catches more sand, which causes more erosion, which deepens the depression. The name comes from early settlers who found these water-holding basins useful for washing, though they obviously formed long before human arrival. After rain, the bathtubs fill with water that evaporates slowly, creating temporary pools that desert wildlife depends on. Some depressions contain layers of sediment from thousands of fillings and evaporations, each layer a record of individual rainstorms. The bathtubs demonstrate erosion operating through subtraction, not the dramatic collapse of a landslide or the sudden cut of a flood, but patient removal of one sand grain at a time, repeated across centuries until solid rock becomes sculpted bowl. The Centennial Mountains march along Idaho's eastern border, forming a section of the Continental Divide where geography determines destiny. Water falling on the north side of this ridge flows toward the Pacific Ocean through the Snake and Columbia River systems. Water falling on the south side flows toward the Gulf of Mexico via the Missouri and Mississippi rivers. The divide is not always a dramatic ridge. In some places, it's merely a subtle rise, a gentle swell where water pauses before committing to one ocean or another. But the commitment is absolute. A raindrop landing inches on one side of the divide will end its journey thousands of miles away from where an adjacent drop lands. The Centennial Mountains were named in 1876 during the centennial year of American independence, though the mountains themselves have stood far longer, raised by tectonic forces and carved by glaciers. The range is not Idaho's highest, but its position as the divide gives it geographic significance beyond its elevation. Elk and moose follow trails along these ridges, passing back and forth across the divide without regard for watershed boundaries. But the water follows immutable rules, every drop choosing, or having chosen for it by gravity and topography, which ocean will be its final destination. sometimes after journeys lasting years as it travels through aquifers, rivers, reservoirs, and countless other temporary homes before reaching the sea. Shoshone ice caves near the town of Shoshone maintain year-round ice deposits, even though summer surface temperatures regularly exceed 90 degrees Fahrenheit. This seemingly impossible phenomenon occurs because of cold air behavior and cave geometry. During winter, cold, dense air sinks into the cave, displacing warmer air and cooling the rock. Ice forms as moisture in the air freezes against cold surfaces. In summer, when surface air heats up, it becomes less dense than the cold air trapped in the cave, so it cannot sink down to replace it. The cave acts as a cold trap, preserving winter conditions through summer heat. The ice formations grow larger each winter as new ice layers add to existing ones, and they shrink slightly each summer through sublimation, but they never entirely melt. Early settlers used these caves for refrigeration, storing food in the constant cold. The caves formed as lava tubes, channels where molten rock once flowed before draining away to leave hollow passages. The tubes have natural openings that allow air exchange but prevent significant warming. Walking into the caves on a hot summer day, you feel the temperature drop within steps, going from desert heat to near freezing in the distance of a single breath. The ice walls glow blue where light penetrates them, ancient cold preserved by nothing more than the weight of air and the shape of stone. The Clearwater River system drains 9,645 square miles of northern Idaho, gathering water that falls as snow in the Bitterroot Mountains and carrying it west to join the Snake River. The watershed is mostly forested, steep terrain where precipitation is abundant and snowpack lingers into late spring. The Clearwater has two main forks, north and south, each draining separate mountain regions before converging near the town of Kuskia. The river's name describes its character perfectly. Unlike many rivers that run brown with suspended sediment, the Clearwater maintains remarkable transparency most of the year, its waters revealing rounded stones on the river bottom even in deep pools. This clarity comes from the granite and metamorphic rock that dominates the watershed, resistant to erosion and producing minimal silt. The Clearwater played a crucial role in the Lewis and Clark expedition, providing the route by which the Corps of Discovery reached the Columbia River and eventually the Pacific Ocean. Nez Perce peoples showed the expedition members how to construct dugout canoes from large ponderosa pines and guided them down the river's rapids. Today, the Clearwater remains an important salmon and steelhead river, though dams on the lower Snake River have reduced runs from historical abundance. The river still runs clear, still carries snowmelt from high mountains to distant valleys, still performs the work it has done since glaciers retreated and water found these paths through stone. Box Canyon. Springs erupts from a cliff face near Hagerman, releasing 350 cubic feet of water per second, the sixth largest spring system in the United States by volume. The spring emerges from a sheer basalt wall, water pouring from multiple outlets and immediately forming a substantial creek that flows a short distance before joining the Snake River. The water comes from the eastern Snake River Plain aquifer, having traveled underground for decades through porous lava rock. The aquifer here meets a less permeable rock layer, and the cliff face where Box Canyon cuts through exposes this transition point, forcing the water to surface. The volume is staggering, enough to fill an Olympic swimming pool every 20 seconds during peak flow. The water emerges at a constant 58 degrees regardless of season, and its consistent flow has made it valuable for aquaculture. Fish hatcheries line the short creek below the springs, using the abundant cold water to raise rainbow trout. The springs have flowed at roughly the same rate for as long as records exist, sustained by the vast underground reservoir beneath the Snake River plain. The name Box Canyon comes from the narrow gorge through which the spring water flows, walls of basalt rising vertically on both sides. Before irrigation depleted portions of the aquifer, the springs likely flowed even more abundantly, but they remain among the most impressive examples of groundwater emergence in North America, proof of the enormous volumes of water moving slowly through rock far beneath our feet. The Lemhi Range stretches along central Idaho's eastern border, containing 51 peaks that exceed 10,000 feet in elevation, yet the range receives relatively little attention compared to its neighbor, the Lost River Range. This relative obscurity stems partly from access. Fewer roads penetrate the Lemhi Range, and its peaks require longer approaches than more popular mountains. But the obscurity also reflects human patterns of attention, how some landscapes become famous while equally remarkable areas remain known only to those who specifically seek them. The Lemhi peaks are just as high, just as rugged, carved by the same glacial processes that shaped the Lost River Range. Alpine lakes dot the high basins, cirques hold remnant snowfields that persist through summer, and the views from summits extend across hundreds of miles of mountain ranges marching toward distant horizons. The range was named for the Lahonti people, mentioned in the Book of Mormon, part of the Mormon tradition of applying scriptural names to western landscapes. The Lemhi River drains the range's western slopes, flowing north through a valley where Sacagawea was born and captured before eventually serving as guide for the Lewis and Clark expedition. The mountains hold both indigenous and settler history, layers of human story written across stone that predates all human presence. The Lemhi Range will outlast all the names humans apply to it, will stand long after current maps are forgotten, indifferent to attention or neglect, simply continuing to be mountains, weathering and rising in the slow dance between erosion and tectonic uplift. Palisades Reservoir covers 16,000 acres when full, backing water up behind a dam completed in 1957 on the Snake River. The dam submerged the original river canyon, transforming a free-flowing reach into a storage reservoir that now holds water for downstream irrigation. What lies beneath the reservoir is a landscape that few living people remember. The Snake River once flowed through here in a canyon with exposed rock walls, rapids, and gravel bars. Cottonwood trees grew along banks that are now far underwater. Before the dam, this reach of river offered some of the finest trout fishing in the region, runs of native cutthroat ascending from downstream. The dam changed all that, creating a reservoir ecosystem with different characteristics: deeper water, more stable flows, cooler summer temperatures near the dam. Lake trout introduced into the reservoir have thrived, growing large in the cold depths. But the submerged canyon remains down there, its topography still present beneath the water, creating the depth variations and underwater structure that fish use. In years of severe drought, when the reservoir level drops dramatically, the old river channel becomes visible again, exposed stone showing briefly before the next season's snowmelt refills the reservoir. The dam was built during an era when converting free-flowing rivers into managed reservoirs seemed purely beneficial, when water storage and irrigation potential outweighed all other considerations. Perspectives have evolved since then, but the dam remains, and the canyon stays submerged, visible only to those with sonar equipment or memories of what existed before concrete walls redirected the river's energy into turbines and spillways. The Pacimaroy Valley stretches between two mountain ranges at 6,000 feet elevation, a high desert basin that receives less than 10 inches of precipitation annually. This is rain shadow country, where the Lost River Range and Lemhi Range wring moisture from passing weather systems before clouds reach the valley floor. What precipitation does fall comes mostly as snow, winter storms that leave a white blanket that sublimates more often than it melts. The valley floor is sagebrush and sparse grass, adapted to drought, thriving on what little water the sky provides. Pronghorn antelope cross this valley in herds, their ancestors having grazed here since the Pleistocene. The air is thin at this elevation, and summer heat feels different than it does at sea level. Intense sunlight but cool shadows, hot afternoons but cold nights. Springs emerge where faults allow groundwater to surface, creating ribbons of green in an otherwise brown landscape. These springs supported indigenous encampments for thousands of years before ranchers brought cattle to graze the sparse forage. The valley's name comes from a Shoshone word, though its exact meaning has been lost to the passage of time and the failure of language to bridge cultures. The Pacimaroi demonstrates how desert can exist at elevation, how dryness is not about heat, but about the absence of water, how life persists in minimal conditions through strategies of patience and adaptation. Crystal Gold Mine near Kellogg descends 7,800 feet below the surface, following silver veins through the labyrinthine geology of the Coeur d'Alene mining district. This is not gold mining despite the name. The real wealth here is silver, lead, and zinc deposits that formed when hydrothermal fluids circulated through fractured rock millions of years ago, depositing metals in veins and replacement bodies. The mine is extraordinarily deep by any standard, reaching depths where rock temperatures climb and ventilation becomes a significant engineering challenge. Miners work in an environment that exists purely through human determination. Without constant pumping, water would flood the tunnels within days. Without ventilation fans, the air would become unbreathable. The Coeur d'Alene district has produced more silver than any other mining region in the United States. Billions of ounces extracted since prospectors first discovered ore outcrops in the 1880s. The Crystal Mine is part of that legacy, its tunnels extending miles horizontally in addition to their vertical depth, creating a three-dimensional maze following wherever the silver-bearing veins lead. Surface operations include massive piles of tailings, crushed rock from which metals have been extracted, that reshape the local topography. The environmental cost of this extraction has been enormous, heavy metals contaminating soil and water throughout the district. But the mine continues operating, following veins ever deeper, human determination and geology engaged in a negotiation conducted in darkness thousands of feet below where rivers flow and forests grow. The white clouds contain more than 50 alpine lakes scattered through high basins, most accessible only by hiking trails that climb 2,000 feet or more from trailheads. These lakes occupy cirques carved by glaciers during the Pleistocene, ice that ground out bowl-shaped depressions in the granite and metamorphic rock. When the glaciers finally melted, water filled these basins, creating lakes that persist because snowmelt replenishes what evaporation removes. The lakes are cold. Even in August, surface temperatures rarely exceed 60 degrees, and thermoclines separate warm surface water from icy depths. Cutthroat trout inhabit many of these lakes, either native populations that ascended from lower waters after the glaciers retreated, or fish introduced by aviation-based stocking programs that dropped fingerlings into remote waters. The high elevation means short summers. Ice can persist on these lakes into July, and fresh snow can fall in any month. Backpackers who make the climb are rewarded with views across multiple mountain ranges and solitude that grows rarer each year as more people discover these trails. The white clouds earned their name from the light-colored granite and quartzite that dominates the range, rock that appears almost white in certain lights, especially when morning sun illuminates peaks still holding winter snow. Split Rock stands near Twin Falls as a landmark that served Oregon Trail emigrants, a basalt formation visible from 20 miles away across the Snake River Plain. The rock earned its name from an obvious vertical crack running through its mass, a fracture created by cooling stresses when the lava that formed it solidified. Basalt shrinks as it cools, and if cooling happens too quickly, the rock fractures, creating columnar joints and linear cracks. Split Rock's fracture is particularly dramatic, creating the impression that some enormous force cleaved the formation in half. For emigrants crossing the dry plain in covered wagons, this landmark provided a reference point, a way to measure progress toward distant destinations. They would see it days before reaching it, the rock's prominence making it visible across the flat terrain. Many emigrants carved their names into the softer rock at its base, graffiti that remains visible today, names and dates from the 1840s and 50s, records of passage by people who never imagined their brief inscriptions would outlast most other evidence of their lives. The rock itself is much older than these inscriptions, formed during one of the many eruptions that built the Snake River Plain over the past 15 million years. It stands now as it stood then, indifferent to the human traffic that passed by its base, a marker in both space and time. The Teton River flows 64 miles before joining Henry's Fork, fed entirely by snowmelt from the western slopes of the Teton Range. Unlike rivers that gather tributaries along their length, the Teton emerges from mountain canyons already carrying most of the water it will have, sustained by snowpack that accumulates on peaks reaching above 13,000 feet. The river's flow peaks in June, when the high-elevation snow finally melts, creating a brief flood season, followed by gradually diminishing flows through summer and fall. By late autumn, the Teton runs clear and low, exposing gravel bars that were submerged during spring runoff. The river carved a canyon through volcanic rock as it descended from the mountains, creating walls that expose layered basalt from multiple eruptions. This is young geology, rock that formed within the past 2 million years, recent enough that erosion has barely begun softening the sharp edges where lava flows stacked atop one another. The river's name comes from French trappers who called the peaks above it Les Trois Tétons, the three breasts, a name that has persisted through generations despite its awkward translation. Bruneau Dunes State Park contains North America's tallest single-structured sand dune, rising 470 feet above the surrounding desert floor. This massive pile of sand exists because of a peculiar meteorological situation. Opposing wind patterns that blow from different directions at different times, essentially trapping sand in one location, rather than allowing it to migrate across the landscape. Northwest winds dominate in spring, pushing sand from one direction. Southwest winds prevail in fall and winter, pushing from another angle. The result is a dune that oscillates slightly, but remains essentially stationary, growing taller as more sand arrives, but never traveling downstream like dunes typically do. The sand itself comes from the Snake River, and its tributaries, granite weathered into individual quartz grains and carried by water before being picked up by wind. Climbing the dune requires effort. Sand gives way beneath each step, making ascent exhausting. But reaching the top provides views across sagebrush desert to distant mountain ranges, perspective that reveals how this accumulation of individual grains becomes a geographical feature, visible from miles away. At night, the dune draws amateur astronomers who appreciate the dark skies and the soft landing the sand provides for telescopes. The sand holds heat absorbed during the day, staying warm long after sunset, creating a pocket of warmth in an otherwise cooling landscape. The dune will stand here as long as wind patterns remain consistent, but climate change or shifts in regional weather could eventually alter the balance, allowing the sand to finally continue its interrupted journey across the plain. The St. Joe River carries a designation often disputed, the highest navigable river in the world. This title requires clarification. The river's headwaters rise above 7,000 feet elevation in the Bitterroot Mountains, and small boats can technically navigate into the upper reaches during high water, though the term navigable becomes generous when applied to narrow channels barely wide enough for a canoe. The designation more accurately refers to the elevation of the watershed rather than the sections where actual navigation occurs. What cannot be disputed is the river's beauty. It flows through dense forests of cedar and pine, its water maintaining remarkable clarity as it descends from mountain sources. The river was crucial for early logging operations, with logs floated downstream during spring high water to reach lumber mills. Log drives were dangerous work, requiring men to ride the timber, using peaveys and pike poles to keep logs moving and prevent jams. The last log drive on the St. Joe occurred in the 1970s, ending a practice that had shaped the river for nearly a century. Today, the river flows past logged-over land slowly recovering, second-growth forests replacing old growth, the river itself having cleaned its channel of residual bark and wood debris. The St. Joe's claim about elevation may be questionable, but its place in Idaho's geography and history remains secure. A river that served as highway and workplace before becoming primarily a destination for fly fishers and kayakers seeking moving water through mountain country. Hell's Half Acre sprawls near Blackfoot, 68,000 acres of volcanic rock from eruptions that occurred around 5,200 years ago. The lava flowed from the Great Rift System, spreading across the landscape as it cooled into various textures, smooth pehoho in some areas, rough AA in others. The field is named for its inhospitable character, land where farming is impossible and even walking is difficult, where the black rock absorbs summer heat and radiates it back until the air shimmers. Early settlers viewed this lava field as wasted space, an obstacle to travel and agriculture. But the lava field supports its own ecosystem. Lichens grow on rock surfaces, somehow extracting nutrients from stone and air. Small mammals find shelter in the tubes and cracks, protected from temperature extremes and predators. Raptors hunt here, searching for movement against black stone. The field's relatively recent age, 5,000 years, is nothing in geological terms, means weathering has barely begun breaking down the rock into soil. Eventually, given enough time, this lava field will be covered with vegetation, like older flows elsewhere in Idaho. But that transformation will take tens of thousands of years. For now, Hell's Half Acre remains a monument to volcanic processes, a landscape that shows what Idaho looked like immediately after lava flows covered the Snake River Plain. Walking across this field, you travel through time, seeing what early humans witnessed when they first arrived in a region still occasionally erupting, still actively being created by forces rising from deep within the earth. Anderson Ranch Reservoir sits near Pine in the Boise River watershed, impounding 413,200 acre-feet of water behind a dam completed in 1950. The reservoir extends miles up the South Fork Boise River, flooding a mountain valley that once contained meadows and forests. The dam was built for irrigation storage and flood control, part of mid-century efforts to manage western rivers for human benefit. The reservoir's elevation, 4,100 feet, means it's surrounded by pine and fir forests rather than the sagebrush that dominates lower elevations. In winter, ice forms across the surface, sometimes thick enough to support ice fishing. Other years, forming irregular sheets that break apart and refreeze. The reservoir provides recreation, boating, fishing, camping during the warm months when access roads are clear of snow. But it also represents the transformation of wild rivers into managed resources, free-flowing water converted into storage that releases on schedules determined by irrigation demands and power generation needs, rather than natural cycles of snowmelt and rain. The middle fork of the Salmon River demonstrates the power of water to carve stone. Over its 104-mile length, the river drops 3,000 feet, creating more than 100 named rapids through a canyon accessible only by river or trail. This is some of the most remote country in the continental United States, designated wilderness, where roads do not reach, and where river runners commit to multi-day journeys with no possibility of early exit. The rapids have names that capture their character: Velvet Falls, Rubber, Tappan Falls, some named for their discoverers, others for their distinctive features. The canyon walls rise thousands of feet on both sides, exposing granite from the Idaho batholith, a massive body of intrusive igneous rock that cooled deep underground before being exposed by erosion. The gradient is relentless. The river seems always to be falling, dropping through boulder gardens and ledges, creating hydraulic features that require careful navigation. The Middle Fork carved this canyon over millions of years, following fractures in the granite, grinding away at resistant rock through the simple persistence of flowing water carrying suspended sediment. Native peoples traveled this river using wooden dugouts, demonstrating skills that modern rafters struggle to match even with superior equipment. Today, the Middle Fork is protected as wild and scenic, its free-flowing character preserved by law, one of the relatively few rivers in the American West that still determines its own course, rather than being interrupted by dams or diversions. Soda Springs lives up to its name, containing naturally carbonated springs where carbon dioxide rises from depth and dissolves into groundwater, creating effervescent water that fizzes like manufactured soda. The carbonation comes from limestone deposits far below the surface, where geological processes release carbon dioxide that migrates upward through fractured rock. Native Americans knew these springs and valued them, and early pioneers marveled at finding naturally sparkling water in the middle of the high desert. One spring was particularly vigorous, erupting like a geyser when early developers drilled into it accidentally while trying to create a swimming pool. The drill hole tapped into a confined aquifer under pressure, and the carbonated water began erupting periodically, creating what's now marketed as the only captive geyser in the world, a natural phenomenon inadvertently enhanced by human activity. The geyser erupts on a timer now, controlled by a valve that allows pressure to build before release. The springs contain dissolved minerals in addition to carbon dioxide, giving the water a distinctive taste that some find pleasant and others avoid. The carbonation is strong enough that bottles of the spring water stored in sealed containers can burst if pressure builds too high. Soda Springs demonstrates how geology continues creating conditions that seem almost artificial in their specificity, how natural processes can produce results that mimic human manufacturing, how the earth contains unexpected variety in the waters it releases from underground storage. The Boise River system drains 4,000 square miles of mountain terrain, gathering snowmelt from the Sawtooth Range, the Boise Mountains, and tributary valleys before flowing through Idaho's capital city at 2,700 feet elevation. The river's three forks, south, middle, and north, drain separate portions of the watershed, each following its own character. The South Fork passes through Anderson Ranch Reservoir, its flow regulated by dam operations. The Middle Fork remains mostly free-flowing until reaching Arrow Rock Dam. The North Fork, shortest of the three, contributes less volume but passes through terrain that supplies consistent base flow. The forks converge below the reservoirs, creating the main Boise River that flows through the Treasure Valley. By the time the river reaches Boise, its flow is almost entirely controlled by reservoir releases, timed for irrigation needs rather than natural snowmelt patterns. Yet the river remains the city's defining feature, a ribbon of water and cottonwood trees creating a green corridor through urban development. Massacre rocks rise along the Snake River east of American Falls, formations whose name suggests violence, but whose geology speaks to ancient oceans. These are not volcanic rocks like most formations in southern Idaho, but rather quartzite, metamorphosed sandstone originally deposited as beach sand 2.5 billion years ago, when ancient seas lapped at shores that no longer exist. The sand accumulated grain by grain, layer upon layer, eventually compressing into sandstone. Then heat and pressure from deep burial transformed the sandstone into quartzite, a rock so hard and resistant that it survives while softer formations around it erode away. The quartzite here represents some of the oldest rock visible at the surface in Idaho, a window into the Precambrian era when the planet was fundamentally different, less oxygen in the atmosphere, no land plants, no animals with hard parts, just microbial life and the patient accumulation of sediments in shallow seas. The rock's current name comes from a misunderstanding of history, an attack on immigrants that probably occurred elsewhere, but became associated with these distinctive formations. The rocks themselves are indifferent to human naming, having existed through such vast spans of time that human history occupies barely a moment of their existence. The quartzite will remain long after all human names are forgotten, still bearing witness to ancient beaches where waves once rolled under skies no human eye has ever seen. The Gospel Hump Wilderness encompasses 206,000 acres of roadless terrain in central Idaho, a designated wilderness area named for a mountain peak that early settlers climbed on Sundays. The name captures a moment of frontier culture, settlers who maintained religious observance even while prospecting for gold, who climbed a difficult peak on their day of rest, perhaps seeking elevation both literal and spiritual. The wilderness itself is a tangle of mountains and canyons, steep terrain where the Salmon River system drains westward toward its eventual confluence with the Snake. The region is part of the Idaho batholith, a massive body of granite that cooled deep underground before being uplifted and exposed by erosion. Forest covers most of the wilderness: Douglas fir, lodgepole pine, ponderosa pine at lower elevations, subalpine fir near ridgelines. The Gospel Hump contains no major lakes, no dramatic peaks, no features that draw crowds. It remains wilderness primarily through its difficulty, its steep canyons and thick forest making travel laborious. Game trails cross the ridges, and elk find sanctuary here during hunting seasons. The wilderness designation protects it from logging and road building, ensuring it will remain as it is, hard country that asks more from visitors than most are willing to give, a place whose value lies precisely in what it lacks: ease of access, development, the softening hand of civilization. Lucky Peak Reservoir backs up the Boise River southeast of the city, its dam creating a lake that extends 11 miles upstream and reaches depths of 330 feet near the concrete wall. The reservoir sits at the transition between mountains and valley, where the river emerges from forested canyons onto the Treasure Valley floor. The dam was built in the 1950s, the last in a series of 3 dams on the Boise River system designed to prevent flooding and store water for irrigation. The reservoir fills each spring with snowmelt, its level rising as mountain snow liquefies and flows downhill. By late summer, after irrigation withdrawals, the reservoir drops, exposing broad expanses of dried mud and stone where water stood months before. The lake is popular for recreation despite its fluctuating levels, its proximity to Boise making it accessible for evening visits. But the reservoir also represents a choice, the decision that managing water for human needs outweighs the value of a free-flowing river, that storage and control justify the loss of whatever existed before the dam. The Caribou Range occupies southeastern Idaho, containing peaks where pine trees grow in twisted, gnarled formations, unlike the straight trunks found in protected valleys. Above 9,000 feet, constant wind exposure shapes the trees, bending trunks, breaking branches, limiting growth to leeward sides. The resulting formations, called Krumholtz or elfin timber, look ancient even when relatively young, trees sculptured by wind into forms that seem to express struggle. These trees survive through flexibility and patience, growing slowly, adding minimal height each year, investing energy in survival rather than competing for space. The wind that shapes them blows predominantly from the west, carrying moisture from the Snake River plain and forcing it upward where cooling air releases precipitation. The Caribou Range receives more moisture than many Idaho ranges, supporting forests at elevations where other mountains show only sparse vegetation. The range was named for the woodland caribou that once inhabited its forests, animals that disappeared from Idaho in the early 20th century as hunting and habitat change eliminated them from their southern range. The caribou are gone, but the mountains that carried their name remain, still shaping trees through wind, still catching moisture from passing storms, still performing their role in regional hydrology and weather patterns regardless of what humans call them or which animals walk their slopes. Warm River emerges fully formed near Ashton, not from snowmelt gathering in mountain tributaries, but from springs that release water at 52 degrees year-round. The river has no headwaters in the conventional sense. It simply appears, flowing at volume from its first moment, sustained by groundwater from the eastern Snake River Plain aquifer. The water traveled underground through porous basalt for decades after falling as precipitation miles away. Chemical analysis of the water reveals its history, trace elements indicating which rock formations it passed through during its subterranean journey. The consistent temperature makes Warm River unusual. Most spring-fed rivers in Idaho are colder, their water emerging at temperatures in the low 40s. 52 degrees is warm enough to feel comfortable in summer, cool enough to support trout in all seasons. The river flows only a short distance before joining Henry's Fork, but in that brief journey, it creates habitat distinct from surrounding streams, an environment shaped by temperature stability that other waters cannot match. Aquatic plants grow thicker here than in colder waters, and insect populations thrive in the moderate temperatures. The river's name is both descriptive and relative, warm compared to snowmelt streams, but still cold by human standards. Temperature that would feel frigid to swim in, but that represents unusual warmth in Idaho's spring-fed water systems. The Albion Mountains rise in south-central Idaho, containing the oldest exposed rocks in the state, metamorphic formations dating back 2.5 billion years. These rocks formed during the Precambrian era, possibly as ocean sediments that were later buried, heated, compressed, and transformed into metamorphic rock. The processes that created these rocks occurred when the Earth was young, when plate tectonics operated differently than today, when continents had different configurations and locations. The rocks have been through multiple mountain-building episodes, each one uplifting and deforming them further. They have been buried and exhumed repeatedly, subjected to temperatures and pressures that would seem extreme by surface standards, but that are commonplace in the Earth's crust. The rocks contain minerals like garnet and staurolite, indicator minerals that form only under specific pressure and temperature conditions, allowing geologists to reconstruct the burial depth and heating these rocks experienced. The Albions are not Idaho's highest mountains, but they are among its oldest, carrying rock that predates not only the Rocky Mountains, but most other mountain ranges currently visible on Earth. Walking across exposures of this ancient metamorphic rock is like touching the planet's deep history, stone that was already ancient when the first simple life forms began leaving fossil evidence, rock that has endured through such vast time that human comprehension struggles to encompass its antiquity. Ritter Island rises 200 feet above Lake Coeur d'Alene, accessible only by boat, its slopes covered with old-growth forests that escaped the logging that cleared most of northern Idaho's lowland timber. The island exists as a remnant, a fragment of the pre-logging landscape preserved by accident of geography, too difficult to access economically, too small to justify the expense of transport. The trees here are massive, some exceeding 4 feet in diameter, western red cedars and western white pines that were already large when settlers first arrived in the region. These trees exist in age classes missing from surrounding forests, representing the structure and biodiversity of mature forests. The forest floor is thick with fallen logs in various stages of decay, nurse logs that support new tree growth, habitat for insects and small mammals, carbon storage that will take decades to fully decompose. The island is privately owned, though its old-growth status has generated interest from conservation groups hoping to secure permanent protection. The trees will continue growing if left alone, adding annual rings that record climate conditions year by year, century by century, slowly accumulating mass and increasing ecological value. The island demonstrates what northern Idaho looked like before industrial logging transformed the landscape, offering a baseline against which to measure the changes that occurred elsewhere. A living museum of forest conditions that were once widespread, but now persist only in protected fragments. The Bruneau River Canyon system branches into tributary gorges, side canyons with names like Jarbidge and Sheep Creek, each carved through 600 feet of rhyolite rock from ancient volcanic eruptions. These canyons are narrow, their walls often vertical, cut by centuries of seasonal floods grinding slowly through resistant volcanic rock. The rhyolite here formed from volcanic ash and lava flows associated with the Yellowstone hotspot as it tracked across Idaho millions of years ago. The rock is fine-grained, pale-colored, composed of the same minerals as granite, but cooled quickly at the surface rather than slowly at depth. Rhyolite is relatively hard and erosion-resistant, which is why these canyons maintain steep walls rather than weathering into gentler slopes. The side canyons are difficult to access, requiring technical rope work or water navigation during the brief periods when they carry flow. Most remain rarely visited, known primarily through aerial surveys and the accounts of the handful of adventurers who have descended them. The canyons provide habitat for raptors that nest on cliff ledges, for bighorn sheep that navigate impossible-looking routes, for plant species adapted to shaded microclimates where direct sun reaches only briefly each day. The Bruneau Canyon system is a hidden landscape even by Idaho standards, remote within remote country, a maze of stone corridors where water has written its signature in vertical walls that will stand long after current rivers have found different paths. McCroskey State Park stretches along the Idaho-Washington border, preserving 5,300 acres of forest atop a ridgeline that offers views into 3 states. The park is unusual for its linear shape, following the narrow crest of the Palouse Range for miles, a ribbon of protected land where old-growth ponderosa pines somehow survived the logging that cleared surrounding slopes. The ridgeline itself is a remnant of ancient erosion patterns, a high point between drainages that has resisted wearing down. From certain viewpoints along the ridge, you can see into Idaho, Washington, and Montana simultaneously, geography defined by political boundaries that overlay terrain indifferent to human divisions. The park was donated by a family who wanted to preserve this forest corridor, recognizing that once such places are logged, they take centuries to return to old-growth conditions. Walking the ridge trail, you pass beneath trees 4 feet in diameter, their bark deeply furrowed, their crowns home to generations of cavity-nesting birds. The forest floor is carpeted with needles accumulated over decades, soft underfoot, absorbing sound until the forest takes on a quality of stillness, unusual even in wild places. The park receives relatively few visitors despite its beauty, partly because it sits between population centers rather than near them, partly because its character is subtle rather than dramatic. It offers no waterfalls or alpine lakes, just forest and elevation, and views across landscapes where human presence remains visible but distant. The Snake River travels 1,078 miles from its source in Wyoming to its confluence with the Columbia River in Washington, making it one of the major rivers of the American West. Of that total length, 591 miles flow through Idaho, the river entering near Jackson and eventually departing near Lewiston, after carving Hell's Canyon along the Oregon border. The Snake drains an enormous watershed, more than 100,000 square miles, gathering water from mountains in Wyoming, Idaho, Nevada, Utah, Oregon, and Washington. The river's name supposedly comes from a Shoshone gesture representing fish, mistranslated by early explorers as snake. The river has many characters along its length. In its headwaters, it's a cold mountain stream. Across the Snake River plain, it becomes a broad agricultural river interrupted by multiple dams and diversions. In Hell's Canyon, it transforms into powerful whitewater, cutting through the deepest gorge in North America. Near its mouth, tamed by a series of dams, it becomes a series of slack water pools resembling lakes more than river. The Snake has been more modified by human activity than almost any western river, dammed for power and irrigation, channeled for navigation, diverted to make desert lands productive. Yet it still exists as a river, still carries snowmelt to the sea, still performs the essential work of moving water and sediment downstream, connecting mountains to ocean in a flow that predates human presence and will continue after current uses are forgotten. Farragut State Park occupies land on Lake Pend Oreille that was, improbably, a naval training station during World War II. Here, 500 miles from the ocean, 293,000 sailors trained for combat, learning seamanship on a mountain lake because its depth and size provided conditions suitable for practicing naval procedures. The base was named for Admiral David Farragut and operated from 1942 to 1946, a brief, intense period when this remote corner of Idaho became a significant military installation. After the war, the Navy abandoned the base, and the land eventually became a state park. Few physical remnants of the training station remain, some concrete foundations, scattered building sites now overgrown. But the land itself remembers its moment of military purpose. The park now serves recreation rather than war preparation, offering camping, boating, and hiking where sailors once drilled. The transformation from military base to state park mirrors a larger pattern in the American West, where lands used intensively for specific purposes are later converted to different uses as needs change. The park's existence depends on that wartime decision to build a naval base inland, a choice that seemed logical given the deep water and isolation, but that now seems almost fantastical, a story that sounds invented, but that left physical evidence of its reality. The Jarbidge Wilderness straddles the Idaho-Nevada border, containing peaks that mark the southernmost extent of Ice Age glaciation in the western United States. This represents a climatic boundary, the point where glaciers during the Pleistocene reached their southern limit, beyond which temperatures stayed warm enough that permanent ice could not form even during the coldest periods. The glaciers that carved cirques and valleys here were small compared to the massive ice sheets that covered northern regions, but they were sufficient to reshape the landscape, leaving U-shaped valleys and piles of moraine that remain visible today. The wilderness is remote even by basin and range standards, a knot of mountains in a region of valleys and isolated ranges. The Jarbidge River drains the wilderness, flowing into the Bruneau and eventually joining the Snake. The area takes its name from a Shoshone word, though its meaning has been debated, possibly devil or possibly a term referring to a legendary creature. Whatever the etymology, the wilderness lives up to any association with difficulty. The terrain is steep, trails are rough and sometimes poorly maintained. Water sources can be scarce in late summer, but this difficulty preserves it, ensuring that only those willing to work for access experience its particular character. Mountains that mark climatic boundaries, that show the limits of Ice Age glaciation, that stand at the southern edge of processes that shaped the northern Rockies. Oxbow Reservoir floods Hell's Canyon to depths of 220 feet, backed by a dam that harnesses the Snake River for power generation. Yet even with 200 feet of water above its original bed, the canyon walls still rise 6,000 feet above the reservoir's surface, creating a perspective that makes the massive engineering of the dam seem almost insignificant against the scale of the gorge. The reservoir is one of 3 created by dams in Hell's Canyon, each one converting a section of wild river into slack water. The decision to dam Hell's Canyon was controversial, generating opposition from those who valued the free-flowing river more than the electricity the dams would produce. But the dams were built, and now the reservoir extends upstream from Oxbow Dam, its still water contrasting with the whitewater rapids that persist in undammed sections. Fish populations changed with dam construction. Salmon and steelhead that once migrated through here were blocked, their spawning runs ending at concrete walls. The reservoir supports different species now, still water fish rather than species adapted to current. Osprey nest on cliffs above the reservoir, diving for fish that never experienced flowing water, born and living in the artificial lake that replaced the river. The reservoir demonstrates how dramatically dams transform rivers, not just slowing water, but changing entire ecosystems, converting dynamic systems into static ones, replacing what existed with something fundamentally different. The Seven Devils Mountains rise west of Riggins, a compact group of peaks reaching 9,393 feet at the highest summits. Early explorers claimed to see 7 distinct peaks from certain viewpoints, though the exact count depends on perspective and which summits you count as separate. The mountains are part of the complex geology, where the Idaho batholith meets older volcanic and sedimentary rocks, creating dramatic relief as erosion works on rocks of different resistance. The Seven Devils form the eastern wall of Hell's Canyon, meaning the Snake River flows more than a vertical mile below their summits. Standing on these peaks, you can see into the canyon's depths, the river appearing as a thin line of silver far below. The mountains hold alpine lakes in high cirques, granite basins carved by glaciers and filled with snowmelt. The area is accessible by trail, though the hikes are steep and long, discouraging casual visitors. The name supposedly comes from Native American legends about 7 devils or demons imprisoned in the mountains, though the story has likely been embellished through retelling. Whatever their name's origin, the peaks are striking, sharp summits that catch first light at dawn, turning pink and orange while valleys below remain in shadow. The 7 devils represent Idaho's topographic extremes, mountains rising immediately adjacent to the continent's deepest canyon, elevation and depth existing side by side in dramatic proximity. Kelly Canyon opens near Riri, containing volcanic features including a collapsed lava tube that creates a natural amphitheater 400 feet across. The lava tube formed when the surface of a lava flow cooled and solidified, while molten rock continued flowing beneath, eventually draining away and leaving a hollow tunnel. Over time, the roof of this tunnel collapsed in places, creating openings to the surface. At Kelly Canyon, one such collapse created a circular depression, its walls formed by the exposed interior of the lava tube, its floor covered with fallen rock and accumulated sediment. The amphitheater shape creates unusual acoustics. Sounds echo and amplify, making quiet voices audible across the entire space. Vegetation has established itself in the depression, taking advantage of the protected microclimate where moisture collects and wind is blocked. The collapsed tube is part of a larger volcanic system that created much of the topography in this region of eastern Idaho, eruptions and lava flows that occurred as recently as 2,000 years ago. Walking into the collapsed tube is like entering a geological cross-section, seeing the interior structure of a lava flow that elsewhere remains hidden beneath the surface. The walls show the ropey texture of pahoho lava, frozen drips and flows that preserve the moment of cooling, stone that still shows the fluid motion it had when molten. The Weiser River flows 160 miles through west-central Idaho, passing through valleys that once served as routes for early mining camps, seeking gold and silver in the mountains. The river drains the western slope of the central Idaho mountains, gathering tributaries from ranges that received less attention from miners than more productive districts elsewhere in the state. The river's path follows geological weaknesses, faults and fractures where erosion works more easily than in solid rock. The result is a valley that provided one of the few reasonable routes through mountainous terrain, used first by indigenous peoples, later by prospectors, and eventually by road builders who followed the easiest grades through difficult country. The river itself is not remarkable for size or beauty compared to Idaho's more famous waters, but it served important roles in settlement patterns, providing water for irrigation and routes for transportation. Small towns along its length, Weiser, Cambridge, Council, grew where the river valley widened enough for agriculture, where tributaries provided additional water for crops. The river still flows through these communities, its water still used for irrigation, though most mining activity has ceased and the valley is quiet now, known primarily to residents and those traveling its length on Highway 95. The Weiser represents the secondary rivers, the watersheds that don't make national parks or tourist brochures, but that nevertheless shape landscapes and support communities, doing essential work without fanfare. Hell's Canyon achieves a maximum depth of 7,993 feet, measured from Devil Peak to the Snake River, making it deeper than the Grand Canyon by more than 2,000 feet. This measurement captures the dramatic relief of the region. Standing on the summit of He Devil in the Seven Devils Mountains, you can look nearly 8,000 feet straight down to the river. The canyon was carved primarily by the Snake River, though glaciation in tributary valleys contributed to the depth by steepening side slopes. The geology here is complex, with the river cutting through multiple rock types ranging from ancient metamorphic formations to relatively young volcanic rocks. The canyon walls expose this geological history in cross-section, layers upon layers representing different eras and processes. The canyon creates its own climate zones. The river level stays relatively warm, while the peaks above receive heavy snowfall. This elevation gradient creates habitat diversity unusual for the distance involved, with desert conditions at the river and alpine tundra on the peaks, separated by only a few horizontal miles, but nearly 8,000 feet of elevation. Hell's Canyon's name supposedly comes from early trappers who found it hellishly difficult to navigate, its walls too steep, its river too powerful. The name fits the canyon's character: dramatic, difficult, extreme in its dimensions and demands. The Payette River system branches into 3 forks, north, middle, and south, each draining separate mountain ranges before converging near the town of Banks. The South Fork originates in the Sawtooth Wilderness, cold water descending through granite gorges before moderating in lower valleys. The Middle Fork drains the western slope of the central Idaho mountains, passing through terrain logged heavily in the early 20th century, but now recovering. The North Fork, smallest of the 3, contributes steady flow from a compact watershed. The 3 forks join to create the main Payette, which flows through a steep canyon before eventually joining the Snake River. The river system provides year-round recreation, kayaking on whitewater sections, fishing for trout, rafting trips that range from gentle floats to challenging rapids rated at Class 4 and 5 difficulty. The Payette's proximity to Boise makes it heavily used compared to more remote rivers, but it retains wild character in many sections, canyon reaches where roads don't follow, and where the river maintains its own schedule of floods and low flows. The river's name honors François Payette, a French-Canadian fur trapper who worked for the Hudson's Bay Company in the early 1800s, another example of European names layered over indigenous geography. Black Canyon Reservoir covers 1,000 acres when full on the Payette River, though its surface area shrinks dramatically by late summer as irrigation withdrawals lower the water level. The reservoir was created by a dam built in the 1920s, one of many storage projects constructed during that era to support agricultural development in the Treasure Valley. The reservoir sits in a transition zone between mountains and valley, surrounded by ponderosa pine and sagebrush, rather than the dense forest of higher elevations. The dramatic seasonal fluctuation creates a boom and bust ecosystem. Fish populations rise and fall with water levels. Shoreline vegetation establishes during low water, only to be drowned when the reservoir refills. The exposed lake bed in late summer shows the reservoir's artificial nature: mud cracked into polygons, stumps of trees that grew before the dam was built occasionally visible, reminders of what existed before concrete walls redirected the river. The reservoir serves its intended purpose, storing spring snowmelt for release during summer growing season, but at the cost of the river's natural flow patterns. Downstream farmers depend on this stored water, their crops only possible because reservoirs like Black Canyon capture and redistribute precipitation that falls as snow in winter mountains. Lemhi Pass crosses the Continental Divide at 7,373 feet elevation, the point where Meriwether Lewis first crossed from what would become Montana into what would become Idaho in 1805. Lewis was searching for the Northwest Passage, still believing that water routes might connect the Missouri River system to Pacific draining rivers. Standing at Lemhi Pass, he looked west, hoping to see easy passage, but instead saw mountains extending to the horizon, a view that contradicted all expectations the expedition had carried about Western geography. The pass is subtle from the Montana side, a gentle rise through sagebrush meadows, almost anticlimactic as continental divides go. But its historical significance far exceeds its physical drama. This was where the Corps of Discovery definitively learned that no water route connected the continent, that the Rockies were not a single range but rather multiple ranges separated by valleys, that their journey would be far more difficult than anyone had imagined. Today, a gravel road crosses the pass, largely following the route Lewis walked. The divide itself is marked by a sign, though water pays no attention to markers, choosing sides based purely on topography. Snowmelt on the west side begins its journey toward the Pacific via the Lemhi River, Salmon River, Snake River, and Columbia River. Water on the east side travels toward the Gulf of Mexico via the Missouri and Mississippi. The pass is a place where history and geography intersect, where human hopes encountered geological reality. The Owyhee River demonstrates the variability of desert streams, carving canyons reaching 1,000 feet deep through volcanic rock, yet often running completely dry in its upper reaches during drought years. The river drains the dry country of southwestern Idaho, Nevada, and Oregon. High desert where precipitation is sparse and unpredictable. Spring snowmelt from the Owyhee Mountains creates the river's main flow, but by late summer, that flow can diminish to nothing in upstream sections, the river reduced to isolated pools in its bed. Downstream, where the river has cut through volcanic plateau, water persists longer, sustained by springs and tributary inputs. The canyons here are spectacular, sheer walls of columnar basalt rising from narrow gorges, but they remain little known because access is difficult and water levels unpredictable. The river's name is a spelling variation of Hawaii. 3 Hawaiian members of a fur-trapping expedition disappeared in this region in the 1820s, and the river eventually carried their memory in its name. The Owyhee flows through some of the most remote country in the lower 48 states, its watershed largely roadless, its canyons visited primarily by rafters during the narrow window in spring when water levels are sufficient to navigate. The river demonstrates the precariousness of water in arid regions, how even significant streams can cease flowing when precipitation fails, how desert rivers exist at the edge of possibility. American Falls Reservoir covers 56,000 acres behind a dam rebuilt in 1978 after the original 1927 structure developed serious cracks. The original dam was an ambitious project for its time, creating one of Idaho's larger reservoirs for irrigation storage. But concrete has a lifespan, and the dam began showing signs of failure after 50 years of operation. Rather than attempting to repair the failing structure, engineers built a new dam slightly downstream, a decision that required draining the reservoir and temporarily exposing the lake bed. The exposed bottom revealed artifacts from before the dam, foundations of buildings, roads, remnants of the town that was flooded when the original reservoir filled. For a brief period, people could walk across what had been lake bottom for half a century, seeing directly the landscape that water had hidden. Then the new dam was completed, and the reservoir refilled, submerging those remnants once again. The rebuilt dam is taller than the original, creating a larger reservoir with increased storage capacity. The surrounding landscape is agricultural. Flat fields of potatoes, sugar beets, and wheat irrigated with water stored in the reservoir. American Falls demonstrates the infrastructure required to support agriculture in arid regions, the concrete and steel needed to capture and redistribute water in patterns different from those that rainfall and snowmelt would naturally create. The Soldier Mountains rise south of Fairfield, their granite cores reaching 10,095 feet at Smoky Dome. These are mountains of the Idaho batholith, massive granite formations that cooled slowly deep underground before being exposed by millions of years of erosion. The granite here is coarse-grained, composed of large crystals of quartz, feldspar, and mica, visible without magnification. The mountain's name supposedly comes from a group of soldiers who explored or mapped the range, though the specific individuals have been lost to time. The Soldier Mountains are not well known. They lack the dramatic peaks of the Sawtooths or the accessibility of ranges near population centers, but they hold their own quiet beauty. Alpine lakes dot the high basins, many of them unnamed, visited perhaps once a season by shepherds or backcountry travelers. The granite weathers into rounded shapes, domes and slabs, rather than the sharp peaks that characterize ranges made of different rock types. Lichens grow on exposed granite, orange and green patterns that advance millimeters per year, slowly breaking down rock into soil. The mountains will erode slowly, granite being resistant to weathering, but eventually these peaks will be worn down and carried away by water and ice, their minerals distributed across valleys and plains, continuing cycles that have already operated for hundreds of millions of years. Crystal Falls spreads across 500 feet of the Pend Oreille River, a broad curtain of white water dropping only 12 feet, but impressive for its width. This is not a plunge pool or dramatic cascade, but rather a wide rapid where the river encounters resistant rock and drops over it in rushing sheet. The falls are best viewed during high water in spring and early summer when the river carries maximum flow. By late summer, flow diminishes and the falls become less dramatic, though the river still drops over the same rock ledge. The falls created problems for early navigation. Boats couldn't pass them going upstream, and running them downstream was risky. Eventually, a dam was built that drowned the lower portion of the falls, reducing them from their original height, but making the river navigable for larger boats. What remains is a modified version of the natural falls, still impressive but altered from their original character. The Pend Oreille River itself is unusual. It drains Lake Pend Oreille and flows north into Canada before eventually joining the Columbia River, one of the few major rivers in the United States that flows toward rather than away from Canada. Crystal Falls marks a geological transition point where the river crosses harder rock formations, creating the drop that became the falls. The rock will eventually wear away under the river's persistent grinding, and the falls will migrate upstream or diminish, but that process operates on timescales measured in thousands of years. The Blackfoot River flows through a valley where lava from craters of the moon reached 15,000 years ago, temporarily damming the river and creating a lake that persisted until the river carved a new channel through or around the obstruction. The lava flow came from the Great Rift, traveling miles from its source before finally cooling and solidifying. When molten rock reached the Blackfoot River Valley, it blocked the river's course, forcing water to accumulate behind the volcanic dam. Eventually, as the lake rose, water found a way around or over the lava, either overtopping and cutting a new channel, or finding a route around the flow's edges. The temporary lake would have created different conditions in the valley: wetlands where dry land had been, habitat changes that affected every species in the ecosystem. Today, the river flows through a landscape shaped by that volcanic episode, its channel influenced by lava flows that are now solid rock. The black basalt gives the river its name, though the water itself runs clear. The valley shows clear evidence of the lava flows, dark rock in stark contrast to surrounding sediments, surfaces that still appear raw and unweathered despite 15,000 years of exposure. The Blackfoot demonstrates how volcanic activity reshapes landscapes, how lava flows can alter drainage patterns, how rivers respond by finding new paths when old ones are blocked. The Pioneer Mountains contain 23 peaks above 10,000 feet, glacially carved into sharp ridges that hold snow well into August. These mountains rise between the Big Wood River Valley and the Big Lost River Valley, forming a barrier that influences weather patterns and divides watersheds. The range is part of the Idaho batholith, more granite mountains eroded into dramatic forms by Ice Age glaciers. The peaks have names that range from descriptive, Hindman Peak, the range's highest at 12,000 feet, to prosaic, Peak 10,930, identified only by its elevation. The glacial carving created cirques and arêtes, U-shaped valleys and moraine deposits that remain clearly visible today. Some cirques still hold small glaciers or permanent snowfields, remnants of the ice that once covered these mountains completely. The Pioneer Mountains are visible from Sun Valley, providing the backdrop for the ski resort and contributing to the area's reputation for snow. The range captures moisture from weather systems moving across southern Idaho, squeezing precipitation from clouds and creating localized heavy snowfall. Water from the Pioneers feeds streams that eventually reach both the Snake River and the Big Lost River, the latter disappearing into the Snake River Plain as discussed earlier. The mountains will continue their slow transformation through erosion, ice and water working to wear them down, though the granite resists this wearing more successfully than softer rocks, ensuring these peaks will stand for millions of years yet. C.J. Strike Reservoir spreads across 7,500 acres of the Snake River, named after an engineer who worked on early irrigation projects in the region. The reservoir was created by a dam built in the 1950s, part of the extensive system of water management infrastructure that transformed southern Idaho agriculture. Unlike reservoirs designed primarily for storage, C.J. Strike was built more for power generation, though it also provides some irrigation benefits and recreation opportunities. The reservoir is relatively shallow compared to some others on the Snake, its broad surface area creating habitat for waterfowl that stop during migration. The surrounding landscape is high desert, sagebrush and scattered juniper, rimrock exposures of basalt from ancient lava flows. The reservoir provides cooling for a power plant on its shores, warm water from the plant discharge creating localized temperature changes that affect fish populations. The Snake River at this point has been substantially modified from its natural state. Dams upstream and downstream, flow patterns dictated by power generation and irrigation demands rather than natural runoff patterns. Yet it remains a river, still moving water downstream, still supporting ecosystems even if those ecosystems differ from what existed before dams. The reservoir carries the name of someone whose life work centered on water management, a reminder that modern Idaho agriculture depends on engineering systems that capture, store, and redistribute water on massive scales. The Beaverhead Mountains march along the Montana border, reaching 11,141 feet at 18 Mile Peak, forming a high barrier that influences weather across eastern Idaho. These mountains capture moisture from weather systems moving eastward, forcing air to rise and cool, releasing precipitation as rain in summer and snow through winter. The range creates a rain shadow effect for areas to the east, where precipitation is notably less than on the western slopes. The mountain's name comes from a rock formation that Native Americans said resembled a beaver's head, a landmark used for generations to navigate through this region. The range is part of the complex mountain systems along the Idaho-Montana border, where multiple ranges intersect and overlap, creating confusing topography, where determining which mountain belongs to which range becomes largely arbitrary. The beaverheads are not heavily visited. They're remote, require long approaches, and offer difficult access. But they serve crucial hydrological roles, gathering snow that feeds streams throughout the region, influencing weather patterns that affect climate conditions across eastern Idaho. The peaks remain snow-covered through early summer, their white summits visible from valleys dozens of miles away. They represent geography operating at its most fundamental level. Mountains gathering moisture, storing it as snow, releasing it gradually as the snowpack melts, providing water that sustains everything downstream. Dworshak Reservoir extends 54 miles upstream on the North Fork Clearwater River when full, backed by the tallest straight-axis dam in the Western Hemisphere at 717 feet. The dam was completed in the early 1970s, a massive concrete structure that transformed a free-flowing river into a long, narrow reservoir. The reservoir is deep, in places exceeding 500 feet, creating cold water conditions even at the surface during much of the year. The dam's height was dictated by the canyon's geology and the need to store sufficient water for downstream flood control and power generation. The reservoir's shape follows the original river canyon, a sinuous thread of water winding through forested mountains. The North Fork Clearwater drained rugged country before the dam, its watershed mostly wilderness where roads barely penetrated. That character persists around much of the reservoir, steep forested slopes descending to water, tributary streams entering from roadless valleys. The reservoir supports kokanee salmon, landlocked sockeye that complete their entire life cycle in fresh water, spawning in tributary streams each fall. The dam itself generates substantial electricity, turbines converting the potential energy of stored water into power distributed across the regional grid. The reservoir demonstrates the scale of infrastructure projects undertaken in the mid-20th century, when building massive dams seemed like unqualified progress before environmental costs and benefits were weighed as carefully as they would be in later decades. The craters of the Moon lava fields contain caves where ice persists year-round, preserved by the same cold-trapping mechanism that maintains ice in Shoshone ice caves. These caves formed as lava tubes, hollow channels left when flowing lava drained away after the surface cooled and solidified. Winter cold air sinks into the caves, being denser than warm air, and becomes trapped by the cave geometry. The cold air cannot escape even when summer heat dominates the surface, so ice that forms during winter remains frozen through the hot season. Some caves contain ice columns and frozen pools that have persisted for decades or longer, growing slightly each winter and sublimating slightly each summer, but never entirely melting. The caves require permits to enter now, protected because early visitors damaged formations and because the ice itself is considered scientifically valuable. Ice cores from these caves contain climate information recorded in annual layers. Walking into these ice caves during summer creates a disorienting experience, leaving desert heat behind and entering an environment where breath becomes visible, where ice gleams in flashlight beams, where the temperature drop happens within steps. The caves remind us that landscapes contain hidden dimensions, that what appears uniform on the surface, black lava rock baking under summer sun, conceals pockets of profound cold preserved by nothing more than the behavior of air and the shape of underground spaces. Lake Walcott spreads across 11,000 acres behind Minidoka Dam on the Snake River, completed in 1906 as part of early federal irrigation projects. This was among the first major reclamation projects undertaken by the newly created Bureau of Reclamation, built during an era when transforming arid lands into agricultural production was considered an unambiguous national good. The dam is relatively low by modern standards, less than 90 feet, but it was substantial for its time, a concrete structure that backed water up for miles, creating storage capacity for irrigation canals that would distribute Snake River water across thousands of acres of desert that would become farmland. The reservoir is shallow and broad, its waters warming significantly in summer, creating conditions where algae blooms turn sections green. Waterfowl use the reservoir during migration, finding food and rest in the marshes around its edges. The dam also generated electricity, though power production was secondary to irrigation goals. Minidoka Dam represents the beginning of large-scale water management in southern Idaho, the start of transformations that would eventually see the Snake River interrupted by multiple dams. Its flows regulated and allocated, its character changed from wild river to managed resource. The infrastructure is over a century old now, contemporary with the era of early automobiles and biplanes, yet it continues operating, still diverting water into canals that make agriculture possible in a region where rainfall alone would support only sagebrush and sparse grass. The Salmon River Mountains sprawl across central Idaho, containing over 200 peaks, many unnamed, in one of the largest roadless areas in the lower 48 states. This is not a single distinct range, but rather a vast complex of interconnected mountains, a knot of high country where determining where one range ends and another begins becomes largely meaningless. The mountains are mostly granite from the Idaho batholith, eroded into rounded forms rather than sharp peaks, though glacial carving has created dramatic features in places. Rivers drain these mountains in all directions. The Salmon River system to the west, the Big Lost River to the south, tributaries of the Bitterroot to the east. The region is more defined by what it lacks than what it contains. Few roads penetrate this country. No cities exist within it. Cell phone coverage is non-existent across vast stretches. This roadless character has preserved it in something approaching its pre-settlement condition, though mining and logging did occur in accessible areas during the late 1800s and early 1900s. Today, much of it is designated wilderness, protected from road building and motorized access, ensuring it will remain as it is. The Salmon River Mountains represent the wild heart of Idaho, country where nature still dominates, where weather and topography dictate conditions more than human desires, where distance and difficulty preserve landscapes simply by making them too hard to develop economically. Murphy Hot Springs releases water at 122 degrees Fahrenheit in the Owyhee Canyonlands, emerging from fractures in volcanic rock far from any human development. The springs are accessible only by long hikes or river trips, their remoteness having protected them from the commercial development that altered many hot springs near population centers. The heat comes from geothermal processes, water circulating deep enough to be warmed by the Earth's elevated temperatures at depth, before finding fractures that allow it to rise back to the surface. The water contains dissolved minerals accumulated during its underground journey, calcium, magnesium, trace elements that give the water a distinctive taste and sometimes leave colored deposits around the spring outlets. The springs create microhabitats where the warm water supports plant species that couldn't survive in the surrounding desert. Steam rises from the spring pools on cold mornings, visible from considerable distances, a beacon of warmth in an otherwise harsh landscape. Indigenous peoples knew these springs and valued them, and occasionally artifacts are found near the springs, suggesting long use by people seeking the water's warmth. Today, the springs remain largely as they were, undeveloped and pristine, visited by those willing to make the journey but otherwise flowing into desert canyons. Their heat and water offered to a landscape that receives both gratefully. The Big Lost River flows north for 130 miles before disappearing into the porous lava rock of the Snake River Plain, never reaching the sea, living up to its name by ceasing to exist as a surface stream. The river begins normally enough, gathering snowmelt from the Pioneer Mountains and Lost River Range, flowing strong in early summer when mountain snow releases its stored water. But as the river descends onto the Snake River Plain, it encounters volcanic rock so fractured and porous that water simply infiltrates downward, sinking into the aquifer below. The river's flow diminishes gradually, and at some point, the exact location varying with seasonal flow volumes, it simply ends, the channel becoming dry gravel while water continues traveling underground. The water doesn't disappear in any absolute sense. It joins the massive aquifer beneath the Snake River Plain, eventually emerging as springs dozens of miles away, where the aquifer intersects the Snake River Canyon. But as a surface river, the Big Lost River lives up to its name, becoming lost in the literal sense, a stream that vanishes into earth. During high water years, the river can flow past its usual sinking point, occasionally reaching the Big Lost River sinks, natural depressions where the last water finally disappears. The phenomenon demonstrates how geology determines hydrology, how the character of underlying rock shapes what rivers can and cannot do, how not all rivers follow the expected pattern of flowing to the sea. Payette Lake spreads across 5,330 acres near McCall at an elevation of 5,021 feet, formed when glacial deposits blocked the North Fork Payette River. The lake occupies a basin scoured by Ice Age glaciers, its depth reaching over 300 feet in places where glacial carving was most intense. The lake is unusually clear for its size, fed primarily by streams that drain granite terrain and carry minimal sediment. The water remains cold even in summer. Surface temperatures might reach 70 degrees during heat waves, but the depths stay frigid year-round. The lake freezes in winter, ice thick enough to support ice fishing, and occasionally even vehicles, though recent warming trends have made ice thickness less predictable. Payette Lake is the centerpiece of McCall's economy, drawing visitors for recreation in all seasons. But the lake predates tourism by thousands of years, its existence determined by glacial processes that ended around 12,000 years ago. The moraine that dams the lake remains clearly visible, a ridge of glacial debris that crosses the valley and forces the river to flow through it rather than around it. Eventually, over geological time, the river will cut through this moraine and drain the lake, but that process will require thousands of years, time enough for the lake to exist through countless human generations. A feature as permanent as any landscape element can be on a planet where everything eventually changes. The Sawtooth Valley contains stretches where the valley floor sits at 6,300 feet elevation, creating conditions where cold air settles and accumulates on calm nights, unable to drain to lower elevations. This creates frost pockets where temperatures plunge below freezing even in midsummer, limiting the growing season to barely 60 days. The valley is beautiful, broad meadows with the Sawtooth Mountains rising abruptly to the west, the white clouds visible to the east. But it's marginal country for agriculture, barely suitable for hay production and prone to devastating frosts that can kill crops overnight, even in July. Early ranchers who settled the valley discovered its harsh character through experience, losing entire crops to unexpected freezes, learning that elevation and topography create microclimates that defy general climate patterns. The valley demonstrates how local topography influences temperature, independent of latitude or regional climate. Two valleys at the same elevation can have completely different frost regimes depending on whether cold air can drain away or becomes trapped. The Sawtooth Valley acts as a cold sink, collecting dense, frigid air on clear nights when radiative cooling drops temperatures rapidly. The result is a landscape that stays frozen long into spring and begins freezing again. In early fall, summer squeezed into a brief window when the sun's warmth finally overwhelms the valley's tendency to hold cold. Island Park Caldera measures 18 miles by 23 miles, a massive volcanic collapse structure formed 1.3 million years ago in what is now eastern Idaho. The caldera formed when an enormous eruption emptied a magma chamber beneath the surface, causing the overlying ground to collapse into the void. The eruption was catastrophic, far larger than any volcanic event in recorded human history, ejecting hundreds of cubic miles of ash and lava, covering much of the western United States with volcanic debris. Today, the caldera is not immediately obvious. It's been partially filled by subsequent lava flows and eroded by hundreds of thousands of years of weathering. But its outlines are visible from aerial views or topographic maps, a roughly oval depression in the landscape. The caldera is part of the Yellowstone volcanic system, formed as the North American plate moved over the Yellowstone hotspot. Earlier calderas in the progression lie to the southwest, marking the track of the continent moving over the stationary mantle plume below. The region remains volcanically active, not in the sense of current eruptions, but in the presence of hot springs, geothermal features, and evidence of magma still present at depth. Island Park Caldera will not erupt again. The hotspot has moved on, but it stands as evidence of the enormous volcanic forces that shaped Idaho's geology, forces that continue operating beneath Yellowstone National Park. The Purcell Trench holds Lake Pend Oreille and extends 150 miles from Canada through northern Idaho, a linear valley carved by massive Ice Age glaciers that scoured the landscape during the Pleistocene. The trench is not a river valley in the normal sense. No river carved it. Instead, ice created this feature, glaciers thousands of feet thick, grinding downward and northward, following geological weaknesses in the rock, gouging out material and carrying it away. When the glaciers finally melted, they left this deep trench, which subsequently filled with water to create Lake Pend Oreille and other lakes along its length. The trench's straight linear form reveals its glacial origin. River valleys meander, following paths of least resistance, while glacial valleys often cut more directly, following the ice's own momentum. The surrounding mountains rise abruptly from the trench floor, their slopes steepened by glacial erosion. The trench collects weather systems moving across the region, its topography influencing precipitation patterns and creating localized climate conditions. The Purcell Trench is named for the mountain range that defines its eastern wall, though the feature itself is broader than any single valley name suggests, a fundamental geographical structure that shapes northern Idaho's landscape and continues to influence everything from weather patterns to wildlife migration routes to human settlement patterns. Huckleberry Mountain rises near Island Park, to 9,613 feet, its slopes covered with the berry bushes that give it its name during the brief window each summer when conditions allow fruit to ripen. The mountain is part of the volcanic terrain surrounding Island Park caldera, built from lava flows and volcanic debris accumulated over hundreds of thousands of years. Huckleberries thrive in the volcanic soil and grow abundantly in the subalpine forests that cover the mountain slopes below treeline. The berries ripen in late summer, drawing black bears that gorge on them to build fat reserves for winter hibernation. Picking huckleberries on these slopes has been a late summer tradition for generations, both for indigenous peoples historically and for modern residents and visitors who brave the bears to gather buckets of the tart fruit. The mountain's name is straightforward, lacking the complexity or controversy of many geographical names, simply describing what covers its slopes. From the summit, views extend across the Yellowstone Plateau to the east and across the Snake River Plain to the south, perspective that reveals the volcanic character of the entire region. The mountain will eventually erode away, its volcanic rock weathering into sediment that will wash into valleys and streams. But that process operates slowly enough that the mountain will stand essentially unchanged for thousands of human generations. The Portneuf River flows 93 miles from the Portneuf Range to the Snake River, passing through Pocatello at 4,462 feet elevation. The river drains volcanic and sedimentary terrain, carrying water that fell as snow on mountains rising above 9,000 feet down to the Snake River Plain. The river's name comes from French-Canadian trappers, though the specific origin and meaning have been debated, possibly a personal name, possibly a descriptive term. The river valley provided one of the routes for early transportation through southeastern Idaho, followed first by trails, then by railroads, eventually by highways. Pocatello grew where the river valley met the Snake River Plain, a natural location for a settlement where routes converged. The river itself is modest. It doesn't carry enormous volumes, doesn't cut dramatic canyons through most of its length, doesn't generate the attention that larger rivers receive. But it serves essential roles in regional hydrology, providing water for irrigation and municipal use, supporting riparian ecosystems along its length, connecting mountains to plains through the steady work of flowing water. The Portneuf represents the working rivers, streams that don't make headlines, but that nevertheless perform crucial functions, moving water and sediment, creating habitat, shaping landscapes through persistent patient effort. Silver Creek flows near Sun Valley with remarkable consistency, maintaining steady flows year-round, despite the summer heat and drought that diminish most Idaho streams. The creek is fed primarily by springs emerging from the volcanic rock aquifer beneath the Snake River Plain, water that fell as precipitation years or decades earlier and traveled slowly through underground rock before finally surfacing. The springs provide base flow that remains constant, regardless of season, supplemented by tributary streams that carry snowmelt in spring. Silver Creek is renowned for its clarity, water so transparent that trout are visible at depths of 20 feet, their shadows on the stream bottom sometimes more visible than the fish themselves. This clarity comes from the spring sources, water filtered through volcanic rock that removes suspended particles. The creek flows through meadows rather than confined channels, spreading across its valley in multiple braided channels that shift position slightly each year during high water. Aquatic vegetation grows thick in the clear water, creating habitat for the insects that trout feed on. Fly fishers travel from around the world to fish Silver Creek, drawn by its legendary clarity and challenging fish. The creek demonstrates how spring-fed systems differ from snowmelt streams, their consistent flows and temperatures creating distinct ecosystems, their reliability making them valuable for both ecological and recreational purposes in a region where many streams are ephemeral or highly variable. The Snake River Canyon near Twin Falls exposes layers of basalt lava flows stacked like pages in a book, each layer representing a separate eruption from different time periods. The canyon walls reveal the structure clearly. Horizontal dark bands of basalt separated by lighter layers of sediment or weathered rock. Each basalt layer tells a story of lava flowing across the landscape from vents that might have been miles away, covering the existing surface, cooling and solidifying, then being buried by sediment before the next eruption occurred. Some layers are thick, representing major eruptions that produced large volumes of lava. Others are thin, barely more than a coating across the previous surface. The total thickness of these stacked flows exceeds several hundred feet in places, representing millions of years of volcanic activity as eruptions built the Snake River Plain layer by layer. The canyon itself was carved by catastrophic flooding during the Bonneville flood around 14,000 years ago, when ancient Lake Bonneville in Utah breached its natural dam and released enormous volumes of water that raced across southern Idaho, carving canyons and creating waterfalls in a matter of days or weeks. The Snake River now flows through the canyon that flood created, a relatively small stream occupying a channel carved by flows hundreds of times larger, maintaining the canyon through ongoing erosion, but incapable of creating it under current flow conditions. Hayden Lake covers 3,850 acres in northern Idaho, with a maximum depth of 175 feet, another glacially influenced lake in a region shaped by Ice Age processes. The lake's water clarity has diminished over recent decades due to algae growth stimulated by nutrient inputs from development around its shores. This pattern, a clear lake gradually becoming more productive and less transparent, occurs commonly when human development increases nutrient loading through septic systems, lawn fertilizers, and other sources. The lake still provides recreation, but its character has changed from the pristine conditions early settlers encountered. The changes demonstrate how lakes respond to watershed conditions, how alterations in the landscape surrounding a lake eventually manifest in the lake itself. Water quality in lakes reflects not just what enters directly, but what happens across the entire watershed, draining into them. Hayden Lake's challenges with water clarity mirror similar issues in lakes across developed regions, illustrating tensions between preserving natural conditions and accommodating human populations drawn to lake shores by the very beauty that development threatens. The lake will continue evolving, its condition determined by management decisions and development patterns, capable of improvement if nutrient loading decreases or further degradation if current trends continue. The Teton Dam site on the Teton River marks where catastrophic failure occurred in 1976, releasing 80,000 acre-feet of water in minutes. The dam was newly completed, beginning its first filling season when seepage appeared in the right abutment. Within hours, the seepage became erosion. The erosion became a breach, and the breach became total failure as the entire dam collapsed. The stored water roared downstream, destroying homes and farms, killing livestock and people, creating a flood wave that reached American Falls Reservoir hours later. The dam failure remains one of the most significant in American history, studied extensively to understand what went wrong. Investigations revealed problems with the foundation. The volcanic rock beneath the dam was more fractured and permeable than engineers realized, allowing water to flow under and through the dam structure. The site remains as evidence, the dam's remnants visible on both sides of the river. Concrete walls that once held back water now standing as monuments to failure. The river flows freely through the breach, having reclaimed its natural course. The reservoir basin that briefly existed is now farmland and meadows again, the landscape having recovered its pre-dam character more successfully than would have been possible if the dam still stood. Freeman Creek plunges through the Seven Devils Mountains west of Riggins, dropping 4,000 feet over 8 miles, creating waterfalls and cascades through a roadless canyon rarely visited. The creek drains a high basin below He Devil Peak, gathering snowmelt and spring water before committing to its steep descent toward the Snake River. The gradient is extreme, 500 feet per mile average, though in some sections the drop is much steeper, creating waterfalls where the creek pours over resistant rock layers. The canyon walls rise vertically in places, exposing the complex geology where granite meets older metamorphic rocks. The creek is small. You could step across it in many places, but its steepness gives it power disproportionate to its size. During spring runoff, the creek becomes a continuous white rush, its roar audible from considerable distance. By late summer, flow diminishes, but never ceases entirely, sustained by springs and snowfields that persist in shaded cirques above. Few people see Freeman Creek. The hike requires wilderness skills and involves significant elevation loss that must be regained on the return. The creek simply does its work, cutting gradually deeper into rock, carrying sediment toward the Snake River, performing the erosive processes that will, given enough time, wear down even these mountains. The Snake River aquifer beneath the eastern Snake River Plain holds an estimated 200 million acre-feet of water in porous basalt, one of the largest aquifers in North America. The water occupies spaces between basalt cobbles and flows through fractured rock, moving slowly southwestward, following the gradient of the water table. The aquifer receives recharge from multiple sources: irrigation return flow, seepage from canals and reservoirs, direct precipitation, and rivers like the Big Lost that disappear into the porous rock. The aquifer is remarkably productive. Wells drilled into it can produce enormous volumes, thousands of gallons per minute from single wells. This productivity comes from the interconnected pore spaces in the basalt, which allow water to move freely through the rock. The aquifer sustains irrigated agriculture across the Snake River Plain, provides drinking water for cities, and eventually releases water through springs where the aquifer intersects the Snake River Canyon. The aquifer is both resource and concern. It's being depleted faster than natural recharge can replenish it. Water levels have dropped across much of its extent, and questions about sustainable use remain unresolved. The aquifer represents water stored over decades, a reservoir created by geology rather than engineering, essential to southern Idaho's economy and ecology, yet finite in ways that require careful management to ensure its continued productivity. Mount Bora's summit sits exactly on the boundary between Custer County and Lemhi County, marking where two jurisdictions meet at Idaho's highest point. This precise positioning on a county line is coincidental. The counties were drawn without knowing exactly where the highest peak would be measured, though surveyors knew the general location. Standing on the summit, you occupy two counties simultaneously, a foot in each jurisdiction, though the distinction is meaningless at 12,662 feet elevation, where county administrative boundaries seem absurd abstractions. The summit is a narrow ridge, steep drops on both sides, views extending across mountain ranges to horizons 100 miles distant. The rock here is ancient sedimentary formations, limestone and dolomite that were deposited in Paleozoic seas and later uplifted, folded, and thrust upward to create the Lost River Range. The summit experiences weather extremes, winds that can exceed hurricane force, temperatures that rarely climb above freezing even in summer, lightning that makes the peak dangerous during afternoon thunderstorm season. Yet people climb it regularly during summer months, following a trail that gains more than 5,000 feet from trailhead to summit, culminating in a knife-edge ridge where exposure demands attention. The county boundary marked at the summit reminds us that human boundaries overlay in different geography, that mountains don't recognize the jurisdictions we impose, that stone predates and will outlast all administrative divisions. The Clearwater River's name comes from the unusually transparent water that results from its source in granite rather than limestone, creating different mineral content than nearby rivers. Water flowing over granite dissolves fewer minerals than water traveling through limestone terrain, remaining clearer because it carries less dissolved calcium carbonate and suspended particles. The difference is visible. Put water from the Clearwater beside water from a limestone-sourced river, and the Clearwater's water appears distinctly more transparent. This clarity impressed early explorers and settlers who named the river for its defining characteristic. The transparency extends throughout the river system, both the North Fork and South Fork, maintaining remarkable clarity, except during brief periods after heavy rains when tributaries carry sediment from disturbed soils. The clear water creates excellent habitat for salmon and steelhead that rely on visual cues to navigate and feed. The river's clarity also makes it popular for recreation. Swimmers and snorkelers can see the river bottom even in deep pools, observing fish and river structure with unusual detail. The Clearwater's name captures how geology determines water quality, how the rocks that water flows over shape its character, how rivers can differ fundamentally based on their source terrain. The river will continue running clear as long as its granite watershed remains intact, its transparency a direct expression of the stone it flows across. Water as messenger carrying information about the landscape it traveled through. And so we complete our quiet journey through Idaho's hidden places, where geology has written its stories in stone and water, where elevation and depth, heat and cold, stillness and motion exist, not as opposites, but as the Earth's patient conversation with itself. These facts ask nothing of us except perhaps to notice, to acknowledge that beneath familiar surfaces run currents both ancient and ongoing, that the ground we walk carries memories spanning billions of years, that every spring and river and mountain represents processes still unfolding. And so we complete our quiet journey through Idaho's hidden places, where geology has written its stories in stone and water, where elevation and depth, heat and cold, stillness and motion exist not as opposites, but as the Earth's patient conversation with itself. We've wandered through landscapes shaped by fire and ice, through canyons carved grain by grain, through mountains that rose from ancient seafloors and valleys, where rivers chose to disappear rather than continue flowing. We've stood where glaciers once stood, where lava once flowed, where water still emerges from darkness into light after journeys lasting human lifetimes. These are not dramatic revelations, but patient truths, the kind that accumulate slowly like sediment, layer upon layer of wonder. Idaho's geography asks nothing of us except perhaps to notice, to observe that beneath the surface of familiar places run currents both literal and ancient, that a spring emerging from a cliff carries water that fell as snow when your grandparents were young, that mountains still grow while we sleep, that canyons deepen, that stone slowly becomes soil, that every landscape is both permanent and temporary, fixed in the moment, but flowing through deep time. As you drift toward sleep, perhaps you'll carry with you one of these fragments: a dune held in place by opposing winds, a lake that remembers glaciers, a river that flows underground for decades before returning to daylight. Let them settle gently, these geographical whispers, these facts that require no response, only the quiet acknowledgement that the earth continues its ancient work while we rest, that stone and water persist in their slow dance, indifferent to our attention, but worthy of our wonder. The landscapes we've explored tonight will be there tomorrow, unchanged in any way we could measure, yet infinitesimally different than they were yesterday. Mountains slightly more eroded, rivers carrying another day's sediment toward the sea, springs releasing another day's share of water stored in darkness. The work continues, patient and endless, requiring nothing from us, asking only that we pause occasionally to witness. Thank you for spending this time exploring Idaho's contemplative landscapes with Midnight Geography. May your sleep be as deep as Hell's Canyon, as peaceful as a mountain lake at dawn, as undisturbed as ancient stone resting beneath unchanging stars. Until we meet again in some other corner of this patient earth, rest well.